Yeah. Dr. Sun, go ahead with your presentation.
Okay. Yeah. Okay. Okay. Good morning, everyone. Yeah, I'm Yuan Xiangsun from China. Yeah, I came from State K Library of Explosion Science Technology, Beijing Institute of Technology from China. Yeah. First, I introduce our university. Our university is a key university in China, and it is located in capital of China. And our lab is a unique state level laboratory in field of explosion science and technology. My topic is effect of aluminum oxygen ratio on underwater explosion load and energy output configuration of a aluminized explosive. This is the outline. Yeah. First one is a background. It's well known is that adding some aluminum powder into explosive is a way to improve the energy of explosive. As a kind of a high performance ideal explosive, the aluminized explosive can the luminous explosive can release a large amount of energy after detonation of ideal component. Yeah, so that the temperature and the pressure of detonation product can be maintained for a long time. Yeah. When it's applied to underwater explosion, it can change the proportion of the shock wave energy and the bubble energy in total energy. Well, the previous research on influence of the ratio on the shock wave bubble load and the energy output configuration is carried out separately. And in this paper, we use the coupled Euler lockdown method to simulate the whole process. Yeah, and the couple effect should be considered. Yeah. And for the CEL, yeah, has advantage of a lockdown and the Euler grid. For the lockdown algorithm having the series, the grid has a series distortion, and for the Euler algorithm, it's difficult to capture the material background, the boundary. These two methods have their own defects and advantages, and the CEL has both advantage of the lockdown and the Euler. The velocity in lockdown boundary provides kinetic energy constant for Euler calculation, while the pressure of the Euler material provides loading force for lockdown region. In CL, the capture of material boundary in Euler material involves the Euler volume method. The CL applied in this paper is based on the central difference method, and the corresponding velocity and the acceleration are expressed in form of displacement. And in CL algorithm, the capture of material boundary in Euler domain involve Euler volume method. And for the state, the equation of state, and in this paper, we choose the USUP equation for the water medium. And okay. And it's established under the condition of incompressive and viscous fluid properties. For the TNT and the aluminized explosive, we use the GWR equation of state. Now we will do the validation of the numerical model by check the characterization parameters. Yeah, for the underwater explosion shock wave, the characterization matter is the peak pressure, attenuation constant, shock wave impulse, energy flow density, and the specific shock wave energy. For the bubble load, the parameter are the bubble pulsation period, the maximum radius, the specific bubble energy, and the formula is given by Cole. Now we do the simulation. Yeah, the The three-dimensional calculation model are established for underwater explosion for SIS-2022 explosion. That this explosive is an aluminized explosive and TNT respectively. Yeah, the explosive which with a mass of the 3 kilogram is placed at the center of the water with a depth of the 12 meters, and we choose a non-reflective boundary condition. Yeah. And here is a shockwave simulation result. The shockwave is basically spherical, symmetrical in all directions, and the pressure on the front surface of outer layers. Yeah, here. And in short time, the order of the millisecond, the shockwave spread rapidly in water. Yeah. And here, the red figure shows the pressure times history, the curve of the shockwave propagation of the aluminized explosive in water at a different proportional distance. We can see after the shockwave pressure by the CEL method reach the peak in very short time. There is still a large fluctuation in the attenuation stage with a double peak or multiple peak. Moreover, the shockwave peak pressure is relatively smooth, which is different from the strong with a strong discontinuous pressure time history curve measured by experiment. This reason is that the CEL method have some defect in capturing the strong discontinuous feature. And here is we calculate the shockwave peak pressure. It's not very different from the experimental value here. Yeah, the calculated value of shockwave impulse and the shockwave energy in a little bit higher than experimental value. Yeah, and yeah, we can see that these two figures. So the calculation result of the three parameters are basically in good agreement with the experimental result. Now for the bubble simulation, yeah, shows that this is the initial bubble. Yeah, initial bubble. This is the bubble expands to maximum volume here. This one is a bubble shrink to the state of minimum value. The last one is a bubble collapse to form a high-speed jet rapidly. For the bubble simulation result, here is we can see the result. Yeah, we can see the result. You can bubble position period and the specific bubble energy show here. Yeah, this experimental is a calculation. From the above validation numerical model on shockwave and bubble, we can see that the calculated parameters such as the shockwave, the peak measure, shockwave impulse, specific shockwave energy, and specific bubble energy are good agreement with the experiment result, which means the effectiveness of the numerical method. Yeah. Now we can use the verified numerical model to carry out the simulation of the whole process of the underwater explosion of RDX-based aluminized explosive with different aluminum oxygen ratio, the ratio of the four ratios, different four ratios respectively. Yeah, and the water area with the depth is 12 meters, area with a vertical distance of 4 meters, and with a different ratio with a one kilogram is placed on the center of the horizon plane at the water of the 4.7 meters. Yeah, we choose the non-reflective boundary condition. Yeah, yeah, it is to it can prevent reflected wave generated by the boundary. Yeah. Okay, here is we show the shock wave. Yeah, we're taking the underwater explosion of RTX, the aluminized explosive with ratio is a 0.36 as example. We show that here. Show that the following figure, which shows the propagation of the shock wave in water medium at different times. Yeah. The following figure shows the shock wave price time history and the phenomenon of double peaks or multiple peaks also occur. Now we can see the influence of the ratio on the shock wave load. With we can see here with the increase of the ratio, shock wave peak pressure and the energy density first increased. These two figures first increased and then decreased. When the ratio reaches 0.36 here, it's 6. When it reaches 6, 0.36, the shock wave peak pressure and the energy flow density reach the maximum. And as to the decay time, distance and the shock wave impulse, these two parameters continue to increase, increase with the increase of the ratio. And we can here is the influence of the ratio on bubble radiance and pulsation period of bubbles. Here. With the increase of the ratio, the maximum bubble and the pulsation period of bubble increase. The reason is that after explosive explode underwater, the water vapor will form at the bubble boundary. With the increase of the ratio, the content of the aluminum powder gradually increased, and excessive aluminum powder reacts with the water vapor during the expansion process, and release large amount of heat. Here is the effect the ratio on energy output configuration. Okay, this means that the proportion of the shock wave energy and the bubble energy in total energy. With the increase of the ratio, the specific shock wave ES increase first and then decrease. And reaching the maximum one, the ratio is 0.36. Okay. The proportion of the specific shock wave energy here, this one, is continuously decrease. And the sum of the specific shock wave energy and the specific bubble energy, this one, and the specific bubble energy EB and the specific bubble energy ratio is keep increasing. And the next slide we will deliver the reason. Okay. The reason is the content of the aluminum powder increase with the ratio. The large amount of the energy in the reaction zone is absorbed by unreacted aluminum powder, and the specific shock wave energy decreased. The energy of the aluminum powder also increased the explosive heat, thus reducing the specific shock wave energy ratio. However, the secondary reaction of the aluminum powder release energy is at the same time scale as a bubble pulsation, so providing the energy for bubble expansion to do work. So the specific bubble energy and the proportion of a specific bubble energy in some energy increased. Okay. Now is the final is the conclusion. First one is the result of the characterization parameter of RS-211 is aluminized explosive, and the TNT and water calculated by CEL method are good agreement with the experimental data. This verify the effectiveness of the numerical method we built. And the calculation results show that the underwater explosion, the specific shock wave energy and the specific bubble energy of RS-211 portion are increased by 35% and 48%, then that was same as TNT. And this means that the increase of the bubble increase of the bubble energy by adding aluminum powder is more than the increase of the shock wave by adding aluminum powder. Yeah, with with the increase of the ratio, the shock wave attenuation time constant, the shock wave impulse of the aluminized explosive underwater increased, and the shock wave peak pressure and the energy flow density firstly increase and then decrease and reach the maximum when the ratio is a 0.36. Yeah. And the shock wave peak measure is insensitive to the change of the ratio, while the attenuation constant, the shock wave impulse and the shock wave energy flow density are sensitive to the change of the ratio. As to the bubble, with the increase of the ratio, the maximum radius and the period of bubble pulsation increased. Yeah. And with the increase of the ratio, the specific shock wave energy ES increased first and then decreased, reaching and then decrease, and it reaching the maximum when the ratio is 0.36. Yeah. And the proportion of the specific shock wave energy, this one, is continuously decreasing. The sum of the specific shock wave energy and the specific bubble energy, and the specific bubble energy EB and the specific bubble energy ratio, this one keep increasing. Yeah. This is my report. Thank you.
Dr. Sun?
Yeah, I'm here.
Can you hear me?
Yeah, I'm here. Yeah.
Can you go to your initial slide where you showed the equations for impulse and decay constants from coal? You had a slide showing the equations, right, from coal.
Pardon? Can you repeat the question?
You had a slide where you had equations for impulse decay from the coal reference. RH coal reference was there, right? You showed a slide.
Can you
go to slide number 5?
Can you tell me which slide, which number slide I can show you and answer your question? Yeah. Which
slide? Can you go to 5?
5. Okay.
Yeah, we'll see.
Which one?
Can you go before? Okay, so how do you calculate impulse? Given a pressure time curve, how do you calculate the impulse?
Pardon, what?
No, how do you calculate impulse in all your validation?
Oh.
Calculate impulse, right? You compare experiment versus theory. So how do you calculate the impulse?
You mean calculate the impulse? You mean this one? Okay. 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 Oh, I see.
Yeah, this slide. Sorry, previous. Yeah. So this one. Yeah. My question is, why do you have that 6.7 theta there in I?
Which one? Pardon?
The first equation, you have 6.7 theta, right? Did you use the same equation for your numerical study also?
Yeah.
Can you say the why you use the same value?
You mean for the different explosive?
No. Why you have used 6.7 theta is my question.
You mean okay? Let me see. You mean here?
Yes, exactly. Yes.
It is just refer to the formula given by the call. Yeah.
Okay. Is there any reason for it? Why we have that number?
You mean the here to be different?
Yes, that number. Why do is there any specific reason why they go with 6.7? Why not 5 theta?
Okay.
No, the reason why I'm asking is when you do the numerical results, when you try to integrate it,
this is a experiment.
Integrate it for the whole. Okay. Then, yeah. Thank you.
You can send my email. I can answer question. Okay.
Sure, definitely. Yeah. Thank you. Thank you. So any questions from audience? Okay. Thank you very much, Dr. So. Yeah.
Okay. Thank you.
Can you log out? Because right now you're sharing the screen.
Okay. Now.
No, not yet.
How can I log out?
Yeah. Thank you. Thank you, Doctor. So next talk is by Suraj Kumar Mandal. You can go ahead with starting.
So the slides are not shared on the Zoom, sir. Please see that the slides are shared on the Zoom, please.
Yeah, give us 2 minutes.
You can start, sir. We got the slides. Thank you.
Hello everyone, this is Suraj Kumar Mandal. I am presenting here the work on comparative study on response of natural and artificial granular media towards blast loading. So this work I have done is in collaboration with Shweta Paunikar and our guide Professor Gopalan Jagdish at LHSR IISc. So the vibrations induced due to any type of blast, be it surface blast, air blast, or any type of blast pose a serious danger to the structures, and this can destroy the structural integrity of those structures. So the reasons for these vibrations are the propagation of high amplitude waves that are generated during the blast. These high amplitude waves are nothing but shock waves or blast waves, as we know them, that they are the energy carriers of the blast. So the objective of this study is to come up with a what we can say configuration of an intermediate media which can act as a energy attenuator of the wave, so that there is no or minimum destruction of the structure. So moving ahead, for the motivation, we followed the thing that since the evolution of modern age war and development of new explosives, people started realizing that there is a need for better designs for structures. But if a structure is already developed, it is very difficult or near to impossible to redesign those structures. So from the times of Second World War only, people started looking into those materials which can act as a cover material for the existing structures, which can attenuate the energy. And one of the most of the type of blast based on the type of explosions. And to perform these street field experiments, it was very dangerous and hazardous also. And there were some repeatability issues related to this type of full field experiments. So people started looking into the more repeatable or reliable experiments which can be done in a laboratory conditions. So shock tube was one of the most was one of the first things that came into the minds of the people, and it was very useful to do repeatable blast experiments. Experimentally, it was found out that with the blast studies of the granular media, it was found out that the peak particle velocity, peak particle acceleration, peak pressure, and peak particle displacements are one of the most important things which can depict the behavior of a granular media towards blast loading. And one of the most important things why we need to delve into this kind of studies is the most naturally available granular media, that is soil. It changes its property from place to place. So for the country like India, it is very essential to come up with a study which can do some help for developing our own shelters in a better way. So to do this study, we used the pre-existing facility at LHSR IISc. It was a vertical shock tube. Generally, we say it as a VST. So it is a twin shock tube facility, and it can operate at a maximum of 100 bar pressure. It has the capability to increase or decrease the length of driver and driven length according to the use. So since we are working with blast waves, so for that reason we use the minimum length of the driver, which was 0.5 meter, and the maximum length of the driven length, which was 4 meters. And the test section that is being shown here, this one was developed for these particular experiments only. And this was square in cross section with 135 cross 135 mm in size. So although the length of the total this test section is 684 mm, but we only used a length of 412 mm for our experiments for granular media. So moving ahead, since this study is about the response, the comparative response of natural and artificially available granular media towards blast loading. So for naturally available granular media, we used abundantly available river sand, which was available in the civil department of IISc. And for artificial available granular media, we used the glass beads. So for sand that we had used was oven dried for 24 hours, and it was sieved till 2 mm, and the size of the glass beads was in the same range, for 1.5 to 2 mm. Experimentally, we found out that the bulk density of the glass bead, no matter how we pour it into the column, it was coming out quite similar to the 43% RD density of the sand, which was 1.63 gram per cc. So to compact the sand to that particular density, we used a method called pluviation. So this is the pluviation setup that we had used. This is the main pluviator. So this pluviation works on the principle of potential energy. This is the simulation that is done at MIT in 1990s for the pluviation. This shows that how higher the height of the drop for the sand particles or the granular media, higher the density of the column that will be achieving. So we had used this pluviation method to achieve the 43% RD of the sand. Moving ahead, when we got our required densities for both sand and granular media, we moved ahead towards the experiment. So this table shows some sample runs, data for some sample runs. Here, this is the test section, CAD design of the test section that we had shown here. So out of these 7 ports that are available, we had used first, second, third, D1, D2, and D3, D4 are the pressure ports that we have used here. And the tables, in the table, PD1, PD2, PD3, and PD4 shows the maximum or the peak pressure at the locations D1, D2, D3, and D4 respectively. Whereas this P star is the maximum pressure that we had got, maximum reflected pressure that we have got at this point, this second. So this second and first sensors or the ports are above the free surface of the granular media that we had used, and all the other sensors are below the free surface of the granular media. The distance between each sensor center in a vertical way is 75 mm, and the second sensor, which is nearest to the free surface of the granular media is just above, so that we can get a proper reflected shock and this proper positive reflected impulse that we are getting here. And this is one of the this plot shows one of these experiments and about how the wave is decaying. So from this experiments, we can see that the intensity of the wave is after entering into the granular media, or here in this case of sand, is decaying along the length in a what we can say in a homogeneous way. But we cannot say the same thing for granular media when the granular media is glass bead, because of these uncharacteristic jumps at random locations. So these jumps were happening for each run, but the locations were varying. Sometimes it was happening at first location, sometimes it was happening at second location, sometimes it was happening at all the locations. So it was quite random. So we didn't know what was the reason for this. So we moved ahead and we plotted, we did some comparison with respect to the what was the reflected intensity of the impinging blast waves. So moving from this, we found out that the intensity of the blast wave was uniformly dissipating, and the intensity of the blast wave or the entering energy in the granular media was not at all decreasing. The reason that we can think of is the lack of particle interlocking in the glass beads because it is hard and it is of spherical shape, and so this can be the reason for this means unavailability of the dissipation in this case. So wait a minute. So to understand it in a better way, we also calculated the wave velocities at each locations for this case. And interestingly, we found out one very peculiar thing, that instead of a monotonic decrease in the velocity, in the wave velocities, when the waves enter, when the wave enter from gaseous media to a heterogeneous media like sand or glass bead, irrespective of the type of irrespective to the type of granular media, the waves were first increasing its velocity to a maximum point, as we can see when the comparison at D1 and D2, and after that the waves were decreasing. So we didn't know what was the answer for this. So to do this, we did some what we can say some experiments to visualize what was happening inside the granular media. So this is one of the video. The left one is for sand, and the right one is for the glass bead that we have used here. And similar blast waves energy that we tried to impose on these two cases, and this is what we found out. So here we can see that for sand, the vibration inside the sand is decaying very fast, where the vibration inside the glass bead is not decaying very fast. The reason from which we can say that since we know that the collision between, since the glass bead is made of quartz, and we know that collision between quartz particles are very near to the elastic collision. So we think that due to this elastic collision, only the intensity of the blast wave is not decreasing very fast in the granular media when it is glass bead, but when in case of sand, it is decaying very fast. And we can also see that the glass beads that are moved ahead means it has gained very much height. So energy is constant for those cases. So after following this, we came to our conclusion that when the glass bead, when the what we can say the granular media is glass bead, the energy will not dissipate irrespective of length or time. But when it is sand, so due to the presence of particle interlocking and all those things, the wave will decay, or the intensity of the wave will decay with along the length also and along the time also. And when we talk about the wave speed, then irrespective of the granular media, when the phase change happens, the wave needs some time to get its peak value in that medium, and after that only it gets dissipated to the minimum value that is attainable. So this was our conclusion, and thank you from my side. If any question, then we can discuss.
Yeah, thank you. So, any question?
Yes, using the pressure only. Visualization we are doing. We are doing the DIC for calculating the wave speed for during the visualization only. Yes. Means these are 6 sensors. So based on all these 6 sensors and based on the locations of these sensors, it is with respect to each other. So we calculated it.
So any questions from audience? Nice work. Can you go back to that video? Probably before that also, that this thing, your velocity values you have plotted.
Is it?
Yes.
Okay. So yes.
S1 is the first sensor, no? Oh, no, it is
This
run number.
Okay. The
This
sensor
is-
locations are D1, D2, D3,
Oh,
and
okay,
D4
D1,
inside
D2.
the sand, inside the granular media to be precise.
Interesting. Because it is going from 721 to 1190,
Yes.
and then coming back to 974.
Yes.
So now go to the video. So when the blast wave is impacting the sand pack,
So first it's
It-
getting compressed, then some expansion is happening due to the reflected wave. Then after that, these things are happening.
okay. So you have placed a sensor at the interface of this, or
Just above the interface. Means we can say that it is an interface. It is 12 mm above the free surface of the sand or
12
the
12
granular media.
mm above the free surface.
What's the?
12 mm above the free surface,
Yes,
no?
yes.
And where is the next sensor placed?
The distance between each sensor is 75 mm. Vertical distance.
75 mm.
Yes.
Okay. I think, so have we calculated the time delay between the first sensor and second sensor?
First sensor, both sensors which are in air.
Time delay in the signals from first and second.
We have calculated, means we have calculated all the times, and there is no, means for the sensor which are in air, there is what we can say, the velocities for both of them are same. But the velocity of change.
No.
The
I'm
time
not
delay
asking
that-
about velocity. I'm just telling about the time delay, maybe in microseconds, right?
Yes.
Okay. Try to correlate that time delay between the velocity of the interface. The interface is moving, no? It is first getting compressed and then it expanded, no?
Sure.
So have you calculated this velocity of interface?
We are doing it.
Please try to correlate these two velocities. I think the velocity is increasing there because of there is a compaction.
Yes, it can be.
Okay, the density may be increasing. So that is what I just don't know, because you need to calculate the velocity of the wave and velocity of the interface. And probably you can get a relation or a correlation the way it is increasing and all. Now it is not, it is something which is it's surprising to me.
Yes, it was surprising to us also. So we are looking into the different aspects. What can be the reason of it? Is it due to just for this experimental setup or something other? So we are looking into it.
Okay, nice work. Thank you.
Thank you.
Yeah. So
Yes, that's a half field. Yes.
For both glass bead and
So density wise, what is the difference? Is there same density for both the materials?
Yes, it is more or less the same density
So
because
what is the
for
value?
glass beads, we were not able to attain different densities.
No,
For-
what is the rough value on this?
What was it?
What is the value of density for sand and the glass bead?
So, for 43% RD of sand, we were getting 1.635 gram per cc, and for sand that we are getting was 1.62, that kind of density.
Okay.
And irrespective of how we pour the sand into the system, the density of the sand sorry, not sand, the glass bead into the column, the
Okay.
density of the glass bead was always constant.
Can you go to the first table where you showed the pressure decay?
This one?
No, the table. Yeah. Yeah. So this one only. So if you see the PD1 to PD4
Yes.
for the trials S1, S2, S3, can you explain the decay? Because 7.68 to 1.3, whereas the
Mhm.
last trial you see 15 to 2.2. Velocity it's random, but here you can see there is a decreasing trend, but the rate at which decrease varies, right? So what do you think?
So it's an exponential decay. It's not a linear decay.
That's what exponential decay. So from 15 to 2 and 11 to 2, right? So even if there's exponential decay, 11 and 15, is there any? So you're saying that velocity is different later, right?
Yes.
Is it anyway getting reflected in a,
This was our one of the observations, as you can see here. So see all the that you said, you pointed out the correct thing only. So we are trying to we are trying to come up with a length normalization also. Here we can normalize the pressure, means peak pressure at a point by the peak pressure of that intensity of the blast wave or the reflected blast wave. But since we are not dealing directly with the explosives, so we cannot directly use those Z values, the characteristic length values. So we are trying to come up with something which can correlate these things, because more or less this comes out to be at a same location, same point, which should not be good.
so what type of sensors you used here?
So presently for these experiments, we have used PCB accelerometer 113B24.
Accelerometer.
No,
Pressure.
sorry, presenter. Sorry, my bad.
So do you think that can we use PCB pressure sensors for solid media?
If it can stick on that, because
The reason why I'm asking is you are going to flush mount it with respect to
Yes.
place, right? So it depends upon what number of particles which are closer to that. So every time when you do a trial, there is going to be difference in it, right?
yes, sir, but means there are something, but doing these experiments, we assumed one thing, that okay, our packing will be
No, the
homogeneous.
reason why I'm asking is this once again goes back to the velocity anomaly which is coming.
Yes, yes, sir.
So how are you ensuring that the values which you get is correct? So then only comes the interpretation, right? No, I understand that. What I'm asking is every time when you take that, how do you know that value is correct is my question. So you have a sensor, pressure sensor, which is for a fluid domain, which measures pressures for air, which is well validated and has been documented. So now when you're using a solid medium, which is maybe granular or sand or any other material, you're placing a pressure sensor inside that medium where the fluid flow is not uniform, for which the pressure sensor has been made. So that is where I just want to know whether you have a way to check whether the pressure sensor is giving proper value for a granular media.
Yes, sir. Because other than this, we cannot.
Okay. Think about it. Repeated run gives you consistency.
Yes.
But what I'm talking about is the accuracy of the value which you get.
Yes, sir.
So you are getting consistency. We are able to
Yes,
see it.
sir.
But yeah, okay. Think about it.
Sure, sir.
Because using pressure sensors in solid medium is still many have not done it, because one of the reason is there is no. That's why they go for forces. When they go for solid medium or any other medium, they talk in terms of forces, so that the quantification will be better. Because if you see the PCB sensors how it works, you will understand why this question comes.
Yes. Okay.
So that is why, yeah. So they have done it 2-3 times, but I don't think that is enough.
Anyways, you can take this point, think about it.
Sure.
Thank you.
Sure.
Nice.
Thank you,
For
sir.
that one only,
Any
I think we are trying a different pressure sensor. One is, I think, because the glass bead, the particle size is assumed to be uniform, but in a sand, it is not like that.
Sand, it is the maximum particle size is 2 mm.
There is a maximum and minimum. Glass is supposed to be same. The packing fraction will be more in sand rather than the glass. It doesn't change at all. As it is, it will be. But there will be a friction between the particles in sand, but not in glasses, hopefully. I think these are the things we have to consider and see how why the decay is coming, etc., etc. I hope. Let us see that.
Sure. Any other questions? Thank you. Thank you, sir.
Thank you, sir. This is forward. This is backward.
Hello.
Morning, everyone. So my name is Suresh Ranjan, and I am a PhD scholar in Indian Institute of Science, Bangalore. So my presentation title is Microstructure and Texture Investigation on Shock Wave Assisted Deformation of Magnesium. So I am working under Professor Gopalan Jagdish and Professor Satyam Subhas. So this is my outlines of today's presentation procedure, and then I will discuss the results and discussion of magnesium that have a CYA ratio is equal to 1.6, and in last I will conclude my topic. So now come to the introduction. So magnesium alloys are used in automobile and aerospace industry due to its lightweight. And during a crash events, magnesium part is exposed to high strain deformation. Therefore, purpose to present work to study the microstructure and texture changes during shock loading or blast loading, and shock induced deformation of a material is a high strain rate deformations. So evolution of microstructure and texture is not a similar in both cases. If you are using conventional processing methods, then it is it is different from high strain rate deformation process. So and one more thing is that if you are using different peak pressure and different time period, then your microstructural feature is changed. So very limited studies are available in literature on microstructure and texture evolution of polycrystalline magnesium. So main goal of this work is to know microstructure of magnesium during shock-induced deformation. So now come to the experimental procedure. So I have received the magnesium in the form of 5 mm thick sheet. So and then I have unidirectionally rolled the sample at elevated temperature at around 200 degrees Celsius. In symmetric manners, and in each pass I have given 10% reductions. So up to 0.5 mm thickness, I have reduced that sample. After rolling, I have annealed the sample at 350 degree Celsius for 1 hour and cut the sample 80 centimeter diametrically. So the disc wire subjected to a high strain rate loading normal to the rolling plane in a conventional shock tube. So actually I have did rolling because of form a basal texture to the normal plane. So This is my rolling direction, and this is my T direction, and this plane is in ND direction. So in ND directions, after 90% rolling, all grains are oriented in same way, and that plane is 0, 0, 1. So this is the basal plane. So in this direction, I have given a shock. So this is the conventional shock tube. In conventional shock tube, there is two parts. So one is called driver section, and this one is driven section. Driven section is fixed at higher pressure, and driven section is lower pressure. So the driven section of the tube was filled with nitrogen gas, which generated the pressure to rupture the diaphragm. And as the critical pressure reaches at a driven section, the diaphragm going to burst out, and compression waves are formed. And after the moving shock front exposed to the disc, which was fixed concentrically at the other end of the driven tube. And my sample is fixed in between two O-rings. So three type of sample I have taken of magnesium. So three type of pressure I have given to magnesium sample. In first case, I have given 0.8 megapascal peak pressure, and in second case, I have given 1.1 megapascal, and third case, I have given 1.5 megapascal. So for achieving 0.8 megapascal, I have used 1 mm thick diaphragm of 16 divisions grooving. And for 1.1 megapascal peak pressure, I have used 1 mm diaphragm of 12 division, and for 1.5 megapascal peak pressure, I have used 8 division grouped diaphragm. In all three cases, I have used nitrogen gas and driven pressure fixed at 1 atm pressure. So pressure experienced by the sample was measured by replacing the experimental sheet with sensor, and maximum strain experience in magnesium at had 8.6% at 1.1 megapascal. Because at 1.5 megapascal, my sample is going to burst out. So only deformation, positive deformation happen in the case of. So this is the processing flow chart. So first I have got starting material 5 mm thick. Then I have did the symmetric rolling and annealing, and then I have performed shock induced deformations in HS22, that is in LHSR, Indian Institute of Science. And after shock deformation, my sample is look like a cap shape and like a heavy spherical cap. So I have cut sample in the direction of rolling direction. So this is my rolling direction. So I have cut sample in rolling direction, and for all experiment, I have performed at the top position of my sample, because I am getting maximum dislocation density and maximum strain at the top position. So actually two type of characterization I have did of deformed sample. For pole figure measurement, for texture measurement, I have did X-ray, and for microstructural characterization, I have did EVST. So EVST is a ACM based technique, and I have got microstructural feature by this characterization. So this is the IQ map, image quality map. So in this figure, it is clearly shows that all grains are very uniform, and grain size is like 75 micrometers, and there is no twins inside the grains in initial sample. So this is the IQ plus IPF map of sample before shock sample and after shock sample. So first sample is annealed sample before shock sample, and this one is deformed at 0.8 megapascal peak pressure, and this one is at 1.1 megapascal peak pressure, and this is the fractured sample. So when I have increased my peak pressure, then twin density is going to increase, and non-uniform grains are formed, and also grain refinement happen in the matrix. And so by this micrograph, I have concluded that the initial sample has a strain-free equilibrium, and formation of deformation twins occurs after shock deformation, which was extensive in nature, and a strain heterogeneity developed within the grains, and there is an overall increase in dislocation density after shock deformation in all three cases. The maximum deformation twinning was found to be at 1.5 megapascal peak pressures. So this is the pole figure. So by pole figure, we have calculated the texture. So up direction is rolling direction, and this direction is TD direction, and the center is a normal direction. So all intensity is concentrated at origin. So it means that all grains are oriented at parallel to normal direction. So in all three cases, but we have when I have increased my peak pressure, then intensity is going to decrease. So initial intensity is 11.9, and after that it is decreases up to 8. So it's really shows that weakening in texture after shock deformation, and the main reason behind weakening of texture could be grain refinement, which has been seen in after shock microstructure. And there is not much changes in texture component apart from reduced intensity. So this is the ODF orientation distribution function. So by this also we have no texture component. So for finer level of a study, we can use ODF, and it's also gives similar component, similar texture component, and it is also clearly says that weakening of texture is happening. Now come to the grain size distribution and micro hardness and tensile property of before and after shock deformed sample. So this is the grain size distribution. So initial grain size 85, and in all three cases, the grain size distribution is going to decrease and non-uniform. So, and right side is micro hardness plot. So I have did Beaker hardness testing along the TD plane, in sample. So where there is a maximum deflection, I have got maximum hardness because of dislocation, maximum dislocation density at this region. So micro hardness was found to be highest at the midpoint deflection region, and it is decreases systematically toward the periphery. And this is the stress ascent curve. So it's clearly shown after shock sample is increased, but ductility is going to decrease a little bit. A strain distribution within the grains. So, after deformations within the grains, a strain is going to increase, and left side, right side is a plot, CAM plot. So in this plot, I have seen that CAM distribution plot shifted by 0.5 degree, that is approximately 10% toward high strain rate. And the strain gradient within the grain having higher value at the grain boundary can be seen. Yeah, so this is the kernel average misorientation. So it is the average misorientation of in test of pixel and neighboring kernel. Now come to the misorientation angle profile. So misorientation is a characteristic of twins. So there generally in magnesium case, three type of twins form. So one is extensive twins, other one is contraction twin, and double twin. So extensive twins characteristic is that it is formed at 86 degree, and CT twins formed at 56 degree misorientation, and double twins formed at 38 degree. So in this case, I have got only extensive twin at 86 degree. So and no significant amount of contraction twins I have got. So this deformation mechanism happened due to basal slip and tension twin. Tension twins. Now come to the conclusion. So in this study, I have got that the shock-induced deformation resulted in grain refinement mediated through formation of deformation twins, and texture weakening was seen after shock deformation. Basal texture decreases with increasing peak pressure, and the grain size distribution clearly indicates grain refinement after shock deformation, or a strength increases after shock deformation of pure magnesium, but ductility going to decrease, and micro hardness was found to be highest where we have that maximum deflection. Thank you.
So any questions from audience?
The ultimate objective is to increase the hardness of the material or strength of the material. Was
Sir,
it?
actually, I want to know what happened when shock is interact with magnesium. So what happened in microstructure, and how texture is going to affect, and how tensile property is going to affect. So all mechanical property and microstructural property I have studied here.
Okay, can you go to the conclusion?
Yes, sir.
Conclusion slide.
So
Strength increases after shock deformation of pure magnesium. What does it mean? Strength increases. when? The last but one. Strength,
one.
strength increases after shock deformation
Yeah,
of
so-
pure magnesium.
So last plot, red one is after shock deformation sample, and black one is before shock sample. So this by this we are clearly see that a strength of magnesium is going to increase after shock deformation.
Okay.
In initial it is around.
Just to understand.
170
Okay, sorry,
and-
I'm trying to understand. Okay, thank you.
So any other questions? Okay, so let me ask.
By how much percent the texture gets weakened? Any
Yeah,
number?
actually, texture, initial texture is around 90%. So actually, here is the intensity. So initially, basal texture is 11.9%, 11.9, intensity is 11.9. And after shock deformation at 1.5 megapascal, it is around 8. So it is, I think, 30% is going to decrease, 20%.
Okay, so based on the strain rate, the texture percentage.
Yeah.
is-
So I have,
So your
I have a texture sample because I have did rolling. So after rolling, a strong texture will form.
okay. Thank you.
Questions? Okay, so coming to the stress strain plot which you showed, right? So in a deformed sample, how you performed, how you obtain the stress strain curve?
Yeah, okay. So for deformed sample, I have cutted very miniature samples. So it is around 2 mm. So curvature effect is not coming in that sample.
Okay.
So length is very short.
Okay. So when you do this strain studies or a microstructure study, which part of the sample, complete entire thickness you study under?
Actually, I have studied at top sections only, sir.
Okay.
Top sections only I have studied.
But if you see the deformation pattern here, you have in the top region tension, bottom compression, right?
Yes.
Did you observe any difference in the microstructure?
Yes, sir. Yes, sir. This is a huge difference at lower periphery and the top positions.
So now, how does the stress strain things fare when you take one at the top versus at the bottom? The stress strain curve which you get is
A stress strain curve I have experiment at only top positions.
you
I have
took
not
only.
cut it at lower position.
Okay. Okay. And other thing is the strain distribution plot, KM plot you showed, right?
Yes.
How do you get the strain distribution? Yeah, this color
so-
plot.
Yeah. So by EVST data, actually it is SEM based technique. So by using EVST, I have plotted this.
No, I'm not talking about the plot. I'm talking about the color 2D contour plot. So that
It's
color
come-
represents.
comes by EVST only.
Okay, it directly gives the strain value.
Yes.
Okay, thank you. Next talk is by Tara Reshma on planar shockwave moving over a double concave ramp.
Good morning, everyone. I'm Tara Reshma, and today I'm going to present a topic, planar shockwaves moving over a double concave ramp. So in general, shockwaves are classified based on the structure or the nature as regular and irregular reflections. Now coming to the classification based on the flow regime, we have steady reflections, where a supersonic flow with a constant property moves over stationary bodies, which gives a reflection which is stationary by itself. Coming to pseudo-steady reflections, where a plane shockwave at constant velocity moves over plane surfaces. So this kind of a reflection mostly are self-similar in nature. They just grow in size with distance or with time. In the case of unsteady shock reflections, this happens when a planar shock wave moves over curved surfaces, a curved shock wave moves over planar surface, or even a curved shock moving over a curved surface. Here, the shock velocity as well as the angle of incidence at every point on the surface changes, which in turn forms a manifestation of shock reflections along the length of the surface. Hence, there is no self-similar nature. Now, coming to pseudo-steady and unsteady reflections, it's very difficult to quantify them or like theoretically study them, because it has a shock which is having a particular velocity or Mach number. Using Galilean coordinate transformation, we convert the moving coordinate system into a shock fixed coordinate system and identify the flow properties and then use for analytical studies. Now, coming to unsteady shock reflections, the initial studies in the unsteady regime was basically to understand shock transition. So basically shock reflection. In the unsteady framework, even today, we don't have a very good proper model which tells us about the shock transition. So Takayama and Sasaki during 1983, they have done very rigorous experimental studies on convex and concave surfaces to understand this transition. So convex surface gave an RR-MR transition, whereas a concave surface gave MR-RR transition. Now coming to analysis where coupled surfaces were used, there was study by skews where a convex surface followed by a planar region of 45-degree plane was used for the transition analysis. Coming to more complex surfaces, such as a coupled concave, convex, and convex concave surface, where both these transitions happen simultaneously, one after the other, using Jiva and Ram et al.'s models. Now, there was another study by Soni and Hajjaj, where they have used double concave reflectors and studied the shock transition in each of these reflectors. So all these cases were considering a shock wave which was moving above the surface in the upward direction. So in our objective of our previous study, we have considered to understand what happens if a shock wave is trying to move downward of a geometry. So we have used the same geometry of Ram et al. And then tried to make a planar shock wave move through it. So these are the instantaneous transitions happening, not the transition shape changes happening to the planar shock wave at different locations of a convex concave natured ram. Now, in this present study, what we are trying to take care is we bringing a new perspective to the entire study. So in the previous study, we have tried to understand what happens to the shock, what happens to the flow, what happens if there is a secondary shock wave which was formed to undertake this change in curvature. But in a new perspective, what we are trying to look at is if a shock wave is made to change its curvature by moving through some complex geometry. Now, how does that shock wave undergoes a transition in a plane region? So in our previous study, what we identified is along the entire convex concave surface, the shock didn't undergo any change in curvature, any change in reflection. Instead, it changed its curvature. Now, a changed curvature shock, when it impinges the plane surface, it immediately changed into an irregular reflection. Now, this irregular reflection, as it moves forward, increased its size. Now, we need to know whether this is a pseudo-steady or an unsteady reflection. So for that, we tried to track the speed of the shock wave with time. And then we understood that along the length, the speed of this shock wave is constant, which was resembling a pseudo-steady nature. But then, finding out the trajectory of the triple point, we understood that it is actually a second order curve or a parabolic nature, which said that the shock wave was continuously changing its reflection. So it was an unsteady reflection. Now, here are some of the possible solutions which we can attain when you have unsteady reflections. In the strong shock reflection domain, where the shock Mach number is more than 2.2, these are the type of reflections which could be formed. One is a regular reflection, another one is a Mach reflection, then there is a transitional Mach reflection, where you will have a specific kink point till which the reflected shock is plane, and after that, it undergoes a curved nature. Now, there's another one which is the double Mach reflection, which has a significant 2 triple points. Okay, so this is called a double Mach reflection. Now, in general, from the Takayama studies and the studies after that, this is how a curved surface undergoes transition. So these reflections are found at different locations of a curved plane. For example, in a concave surface, the initial reflection will be a simple Mach reflection, followed by a transitional Mach reflection, double Mach reflection, and a regular reflection. In the same way, RR to MR transition happens across a double Mach reflection and a transitional Mach reflection. Now, coming to the weak shock reflection domain, here the reflections are completely different. So the irregular reflections, so we have regular reflection and other irregular reflections are, one is a simple Mach reflection, which is just like any other simple Mach reflection, whereas you have von Neumann reflection, Vasilev reflection, and Guderli reflections. So these are reflections obtained by the standard and non-standard solutions of 3 shock theory and 4 wave theory. So these are the possible solutions we can get if we have a irregular reflection transitioning in an unsteady framework. Now, here are some of the results where we have identified such transitions and such reflections. So in the strong shock reflection domain, we have identified a transitional Mach reflection, not very much quantified as such, but looking at the structure, we could say that these are the transitional Mach reflection and double Mach reflections. Now, just as I said, we had to understand or try to quantify these reflections. For that, we have used the quasi-steady assumption. So every instant is considered as a quasi-steady or a stationary reflection, and then using Galilean coordinate transformation, we have tried to find the flow Mach number incident shock angle, which are enough to draw the shock polars. So what we understood is that as the irregular reflections moves along the length of the plane, the theta or the angle of the incident shock wave, the free stream and the incident shock wave, so is deflected and the flow deflection angle reduces. So this is the way in which the propagation of theta happens, and it changes just like every solution of a that you can attain in a shock polar. So these are some of the cases shown for mark number 2.6 and 3. Now coming to weak shock reflections, we also obtained, or we have also tried to simulate a few cases for weak shock reflection domain. So at m equal to 2 or shock mark number of 2, we have obtained a lot of solutions, and then we tried to pick some of the reflections. So initially the theta was larger, and along the length of the ramp or the plane section, theta was reducing. So there was a visible transition from a Gooderly reflection, which is analytical result. So this was plotted using a four-wave theory in the shock polar. And then there was Vasilev reflection, von Neumann, and simple mark reflection. So all kind of reflections are possible to be seen in such a study. So in our present study, we are trying to take this to to new different geometries. So one such case is a double concave surface, which is a similar geometry as used by Hajjaj and Sony. So it is of a radius of 50 mm. So simulation was carried in the InVisit framework using ANSYS Fluent and structured grid. So our study gave us different changes in the planar shock wave as well as the flow structures. So we were mainly interested in what happens to this planar shock as it moves along the concave, double concave surface. So it is found that after the end of the first concave section itself, there was a small reflected shock or weak reflected wave formed here. And as it moves further to the second concave surface, it apparently forms a mark wave, mark stem, and a very weak reflected wave. Now, this mark reflection structure, as it immediately touches the planar region, it's still undergone an irregular kind of reflection, which grows in size further. Now, two things to be understood is if this is an irregular reflection or an unsteady reflection or a pseudo-steady reflection. So first thing to identify is whether the speed of this shock is constant. So using this study, we understood that the speed of this shock wave was constant. Next thing is to identify what is the triple point trajectory. So for one such case of 1.4 Mach number, we found out the triple point trajectory, and the trajectory was found to be non-linear. So it also says that the planar shock wave undergoes unsteady reflections along the plane surface of the ramp. Now, for different other Mach numbers, we have found a similar variation. So the future study is now to understand for different surfaces how the irregular reflection is behaving in the unsteady framework. So basically, a planar shock wave undergone curvature change, and then it behaved as a planar, unsteady reflection. Now, all these studies says that the planar shock wave, which is hitting the plane region, has a history to it. So it is not like the canonical problem where you have a blast wave of circular or cylindrical or spherical structure which interacts on a plane surface. The problem is little more difficult to deal here because it has a history, and this history depends on the shape ahead of it. So the current perspective is to deal with such shock waves, to understand the transition of such shock waves and see if there is any kind of correlation. That's it. Thank you very much.
Any questions from audience? So
So what is the flow Mach number after the shock? There was a shock Mach number of 1.9.
Yeah.
What is the flow Mach number behind the shock?
So it will be supersonic, but I don't know exactly right now. It
Is
will
it
be lesser
supersonic?
than this shock Mach number. We can
So-
actually find it using
Yeah,
the
of course.
Galilean
Is
coordinate.
it going to be supersonic? Are you sure it's supersonic?
Yes, mostly like in the previous geometries, like 1.2 ms gave us a subsonic flow, but not every location will have a supersonic flow. It depends on the curvature of the shock. Actually, we have a completely unsteady flow behind the planar shock wave. The reason is if you here, so if the planar shock wave is initially moving here, it changes its curvature, but it is creating a flow downstream, so which can be found out using the Galilean coordinate transformation. Actually, do not recall the exact value, but what happens is there is a sharp expansion corner followed by flow separation regions, which later forms some stationary secondary shock waves. So the entire flow region is completely two-dimensional, and it has a lot of changes. So the flow here itself will be a combination of both subsonic and supersonic, and the Mach numbers change according to the shock speed.
So when you say supersonic, are you talking about lab frame or shock Galilean transformed frame?
In the transformed frame. So that is how we will be plotting the shock polars.
If it is supersonic in the transformed frame, that does not matter because your expansion fans will depend on the flow Mach number in the lab frame. So it should not matter if you have a supersonic flow in the transformed frame.
Yes.
So when you say supersonic flow, I really doubt that. And I will also tell you why I doubt it again. In the lab frame, if you have the solution for the shock tube problem is that at infinite shock strength, the Mach number downstream of the shock in the lab frame is 1.34.
That's right.
So something to consider.
Yeah. So I'll go back to the previous study and say that when MS was 2, the M0 we got was lesser than that, but I'm not sure what it exactly was. That is how we plotted these shock polars. So I'll look into the aspect that you have talked about. But what we will look at is as a irregular reflection is formed here, and what is the flow Mach number? I mean, we'll be just looking at the speed of this shock wave in the plane section and transform it, because we are not concerned about what flow happens here. But if a irregular reflection is formed here, that particular speed will be used for transforming.
Right.
Yes.
I also agree with him that it should be subsonic. Okay. Anyways, when we look at this flow compared to a single curve, when you have double curve, this concave curves, two of them.
Yes, sir.
The change, is it in the final shock that's running through, or is it only in that corner?
No, we are what basically happens is planar shock wave changes its curvature. The reason is that at every point, the foot of the shock will be perpendicular to the surface. So it undergoes a curvature change. Now, such a changed curvature shock now moves over a plane surface. So that is our new concern. So this irregular reflection is being studied for transition.
But I still see that the shape, everything seems to be same as a single curve, right? Single concave. The shock shape is all same.
No, sir. Actually, you can see here, it becomes an MR. I mean, a small reflection.
No, that is near
Yes.
that place. When
Yes,
I go outside that
Okay.
concavity,
Mm.
say 370 microseconds after,
Yes.
the shock that's running through,
Mm.
the main shock,
Yes.
that doesn't have any characteristic
No, but
change.
so basically, in the previous case, the previous geometry, but it has the history to it. So that's what we are looking at. So if this shock wave initially curves in the opposite direction for the concave nature, because it needs to have a perpendicular.
That's fine.
Yes. So a curved shock which was curved twice now undergoes an irregular reflection. So our interest is, we have not tried to analyze it in a further stage. It's just a study in progress. We're just proposing that if there is something which is interest to us in the irregular, unsteady.
Yeah, that's what
frame.
I'm also
Yes.
asking.
Yes.
Basically, like you have a single concave surface versus double concave surface.
Yes.
Now, if I put something purposely in the flow,
Okay.
okay, will I be able to shape the shock that's going through? That's the question I'm asking, essentially.
Purposefully. And any other obstruction you are saying?
Yeah, I can put, say,
Yes.
5 different concavities
Yes.
if I want.
Yes.
But will that give me a particular shape that I want
At the end,
at the end, after this whole thing goes past this body that I put in?
we have not done it so far, but our idea is to do a parametric study of different shapes and then understand if there's any kind of influence. So if we have a very curved shock and these kind of shocks, whether the reflections are different or
So what you currently say as there is a history is all happening only in that that trailing shock that's sitting there, right? Which is having a connection with the body, right? That's the only shock that's going to have an effect.
No,
main
the
shock that
entire
runs
plane.
through currently doesn't seem to have much effect.
Okay. No, what our idea is, if a shock has a particular history, we have to know whether that history, because people have in literature quoted about the history of shock transitions, like the history of a shock which was moving through surfaces. But nobody has properly said anything on the reflections it forms. So if there is a history, we are just trying to see.
Yeah, so it comes down to whether you have something happening inside behind that, and they are sending some waves to this, and so that area behind is going to have some effect.
Not only that, also about the shape of the shock.
Yeah, but
Yes,
is there a
yes.
change in shape of the shock
Yeah,
is what I
that's
asked.
right.
Okay, and you have to find out whether it has a shape change.
Right.
Okay.
No, see, there can be variations along the length of the properties of the shock can vary along the length of the shock. It's not just the curvature.
That's
The
right.
shock strength can change along the length. The
That's
properties
right,
of the
sir.
shock can change along the length.
Along,
Along the height. What I mean
Along
is
the
along the
height.
height.
If it is a planar shock, that doesn't change. But this is a curve shock, so there may be 2D flow behind.
No, that's what I'm trying to say. So once you have gone through this, whether you go through a single curvature, from what I understand right now,
Okay.
you have confirmed there is history. And
Ah.
at this point, you're going to start studying.
whether that history
Right,
really
and
matters.
The issue of whether from the right-hand side, you can predict what it came from is a deeper query. It's a
Yeah, correct.
Can you just go to that where you showed those parabolic variations? So a good place to start would be those series of curves. No, it looks like you had a family of curves. No, right at the end, last but one slide. You can collapse it maybe with.
Yeah,
some
you
kind
mean
of
the
a-
triple point trajectory?
Yeah. This will collapse. Isn't it?
Yes,
You've
yes,
tried
yes,
that.
I don't think that will collapse. It's not a similar problem. Unsteady
They
reflection.
are for different Mach numbers.
Okay.
Yeah, we
okay.
can scale it. Non-dimensional. Yes, non-dimensional.
And other thing, Tara, I think we have to look into that. I think the Mach number is not supersonic. It's 0.9.
Okay.
For 1.9 shock Mach number.
No, I've actually
the
not
F2 flow is
calculated.
0.9 only. I don't know how you are getting an expansion fan over there.
Okay.
So you have to look at that carefully.
Yes. No, actually the same thing happened in the previous results also. What we understood is the flow itself is not having a constant velocity. It's completely unsteady by itself.
No, that is not the
Yeah.
problem. You have the initial
Right. I
this
understand.
thing.
Ah,
No, the
yes, sir.
flow coming then. Probably the flow may be going slightly 0.9 to it may be going slightly transonic behind that when it passes over that sharp curve. But expansion fan, I don't find the reason for expansion fan there.
Yes.
It may be supersonic patch forming by some other reasons. I don't know.
No, sir. In the previous study, where we had convex concave structure, even for 1.2 ms Mach number, we see that as the plane shock moves further and further downstream, we see supersonic patches formed in the, so instantaneously, if you take the shock relations and all, you won't be able to find that the downstream Mach number is supersonic. It will be, but as the planar shock wave moves down, we understood that the unsteady flow also accelerated.
No,
This was actually
it-
results from the previous study.
It won't accelerate if it moves over a plane surface, right? It will accelerate only on a convex ramp.
That's right.
Yeah, convex ramp you will have.
I'll have a look.
Yeah, please check that.
Sure.
Any other questions?
Thank you.
Reached the end of the session. I would like to invite Professor Gopalakrishna Hegde from IIC Bangalore to present a memento to our session chair, Professor Aragappan. This is a quick announcement to the delegates. So the second session will end by about 12 o'clock with the valedictory ceremony. And after that, we would be packing lunch and leaving to the conference store and then banquet. So probably by 12 o'clock, we'll be planning to leave from here. And we'll be going to Dakshina Chitra with a visit, and then we'll be reaching the banquet place by about 5 p.m. or so. And we'll be starting from there by about 9:45 p.m. Now we can break for tea. Probably we can come back after 15 minutes. Lunch will be packing. Sir. Yeah. Yeah. Thank you all.
Check that.
Hello. Hello. Yeah, your voice is breathing, but I can hear, but it's a bit breathing. Yeah. Yeah, now it's okay. Slight Etho, I think. I don't know where the Etho is. I think you have to check the system's speaker. Okay, you just tell me. It's still Etho is there. I don't know where this Etho is coming from. Shall I present my screen and see? Can you check your system's speaker where this you are presenting? Maybe I think Etho is from that screen itself. Still, I cannot hear properly. So it's just like Etho and. Just try my screen. I don't know. Is the screen visible? Yeah, I think I can see. And you just put the full screen mode. Fine. Is it fine now? It's in slideshow mode only. Yeah, I'll just continue.
Hello.
Yeah.
Hello. Is it Professor Dr. Pradeep?
Yes, sir.
Dr. Pradeep, your audio is very clear to us. What's the problem?
No, video, I think.
No, video power say I'm just seeing the slide of working principle now.
Yes, so it's.
I'm seeing
GIF
the
is
animation
fine.
also. I'm seeing the animation.
Okay. I'll just check the video once. Video is running properly now?
Yeah, perfectly all right. I'm seeing the critical flow regime, primary shock structure, recompression shock structures, mixed flow regime, primary shock structures.
Yeah, sir.
I can see white and gray. It's not colored, but it's black and white. There's an animated animation scene. Yes, I can see the video.
Yeah, I think then it should be perfect, I think.
Yeah, the only thing is be careful that don't log in on another device when you are on this device.
Yes, sure.
Okay.
Yeah,
Otherwise, everything is perfect.
Yeah, I have logged in through my laptop, so there's no other device.
Very good. That should be all right. Can you show me your face, because I want to see most of them don't keep their camera proper.
Okay, I'll just check. Where this? I have to unshare. Okay.
Yeah, correct. Perfectly all right. Yeah, I just saw you for a brief second. You're all right.
Okay, sir. Thank you.
Yeah. All right. Very good. Thank you.
Yeah. Thanks.
Shock interaction symposium, SIS-2022. Starting with session 1. And sessions are will be Professor Pandey from the Department of Economics of Madras. Welcome, sir. Very good morning, all of you. I think welcome to the last session of the conference. So we are there. Instead, we are starting with load. All of you can take the books and complete it. Okay. First, let me call Mr. Sanjeev Kumar. The excellent study of hypersonic double flow. All of you, I'm Dr. Swarup going to measure this is seminar, experimental study of hypersonic double flow. In the double spread of geometry when subjected to hypersonic flow, there are a lot of complex flow profile can be seen. So this is where we can see that the separation for public shock and shock to shock interaction. Due to this phenomenon, large error fundamental shockers and changing condition are rapid. Our experimental setup. So this is our experimental condition. So that section they are experiment so that this time can be started. So hypersonic double cone flow. So double cone model has been fabricated with dimension of so our main is to analyze the local analysis and study of the so the practical products of this experiment is designed by central body. So during the experiment, silver numbers have been taken with sampling of 79 information 25 pixel and so first we can show that working on the center time. So we were the mass, so that the and the separate background so we show the transfer stage to bring out that we have the solution for ground state so the wave service the second round influence the function of the junction of that information. The fact that situation levels is influenced by the formula due to the second round. So when information round observe the second round the shoulder of that round is equal to 7 minutes Same way seen from at least from which 1.5 comes in India. So using this analysis so this plot shows the energy content of first and special mode of the present flow. If you will notice that the first mode captures 90% of energy of flow. So we can say that it's a very complex flow pattern for a lower range of theory analysis using and this makes it shows here the same show the second shot extension from within shown here. While in the second figure, the 5.5 shows the separation part, the 6 shows the regulating plans. This during the round 7, the reflected shock wave is estimated from secondary triple line, which is present out point 9, which is showing the reflected inflection points. So, with plot of the time state temporal coefficient of first mode of the shown here, without the flow stable frequency, low frequency, that is the time of the high frequency frequency. So after this simulation, I will estimate the surface flux around the constant case. So that when we look at the thermodynamical movement of this flux in how small our three diagrams. So firstly on the cone, and then we subjected to a experimental setup, and their tangent temperature has been recorded by using a data acquisition system. After that, using a code, using these tangent temperatures, the heat flux has been estimated for every eight different position of the cone, which has been shown in this figure. So the conclusion is that time evolution of Selenium image of the flow field pattern appears to be a similar eddy type 5 shock iteration. The double oblique cone has been generated by second cone interaction with the boundary layer developed by first cone. The energy content of special mode shows that the 90% of energy flow field captured by first mode. The heat flux measurement play important role in design aspect of aerodynamics vehicle. And it would be very interesting to investigate the origin of flow pattern and unsteadiness using surface measurement. Thank you.
He has given audience a lot of time. Probably you can interact more. Any question, please?
EOD slide.
Yeah.
Can you go to that?
EOD.
This one.
Yeah.
Okay. What is the time correspond in the right figure?
Yes, time. Test time.
Versus frequency, like what?
Yeah, yeah.
Exactly.
Time versus frequency.
So, I mean, this is for the Selenium snapshot, right?
Yeah, yeah.
So you would have, like, how did you do the POD? Is it for the entire time? For the all snapshots? Or you have divided the time and?
Yeah, we divided.
So like dividing and averaging kind of.
Yeah, time average.
Okay, like I want to understand this plot where you're plotting time versus frequency and the POD contours, right? So why is it time versus frequency?
Okay.
Just wanted to understand that plot. Can you explain it?
Actually, I don't have answer now, but I will give you. Okay.
Hello, excuse me. Hello, how is that heat flux is being calculated? Heat flux.
Sir, firstly, we develop a coaxial thermocouples.
Okay, what methodology is being used for calculating that heat flux?
Yeah. What's that?
What methodology is being used to calculate that heat flux?
Actually,
I'm
we
asking.
have an equation related to temperature and heat flux, Duhamel superposition integral.
Can you tell me what is that equation, sir?
Equation I don't write here, but yeah, it's available in literature actually. So we curve fit. Actually, we discredit that equation by using cubic spline method, and then we estimated heat flux from measured transient temperature from fabricated coaxial thermocouple. It's inverse interpretation.
We can make out where the heat flux.
You should give it respect to length,
Geometry, yeah.
non-dimensional length of your geometry rather than sensor location.
Okay, sir.
Okay.
Thank you, sir.
So, any more question, please? Okay, this study you have done at what enthalpy level?
What's that?
What enthalpy you have done it?
Enthalpy. Enthalpy. 0.9. Total enthalpy is 0.69 megajoule per kg.
Okay, okay. If no other question, I think you can give a big hand.
Thank you, sir.
The next paper is not there. That is Varun and Ram Prabhu. I think nobody is there. Let us go to third paper. That is Arun Kumar Perumal and Radhakrishnan. Shock manipulation of supersonic jet via fluidic injection.
So, good morning. So the talk for today is like the shock manipulation of a supersonic jet via fluidic injection. So this talk essentially like focus on brief limitations of use of fluidic injections for jet manipulation, like in the sense of replacing the conventional passive techniques. So the idea of replacing the conventional passive techniques is that like there are limitations on the cost wise and and apart from cost, like adapting to different scenarios of flight durations. So the replacement comes with the fluidic techniques with certain advantages, and there are a lot more limitations to it. So one such schematic of a nozzle is being put over here. So there is a convergent divergent nozzle, and these red ones are the injectors where we can inject fluids into the nozzle. For these fluidic injections has been applied to multiple scenarios of like airfoil flow separation, thrust vectoring, mixing, acoustics, and multiple such applications. But the key is like still it's in the development stage because of few limitations, which you will see it. So the one limitation is like the injection pressures, like what we feed it to the injectors during the laboratory cases are pretty much larger than the nozzle operating pressures. Okay. But that is very good take in laboratory conditions. We can manipulate the injection pressure sufficiently larger than the nozzle pressures. But when you want to put it in actual situations or put in a practical applications, so the injection pressure, which is actually driven from the main engine, has a limitations on the maximum cap. So that is where like the injection pressures has to be sufficiently lower than the nozzle pressure, if at all like these fluidic injectors has to be really put into use for certain applications. Okay. And the second limitations, what we see is like the mass which has been pumped from the main engine to the fluidic injectors. So if you see like in laboratory conditions or people who are reported in literature, we say like one can drop over like 10% of the mass or 15% of the mass, like when we do the laboratory, and we see substantial benefits either in terms of noise or in terms of vectoring or any such application. But like when we put into an actual engine, like I cannot withdraw or blade about like 10% of the mass and pump it to the fluidic injections. So if I do that, like only 85% of the mass goes to the engine, and there's going to be a significant loss in thrust. So one cannot bear that. So there is actually a cap on that as well. So one can actually bleed about 5% of the mass from the engine and bleed it to the fluidic injectors for making those manipulations. Okay. So this present talk mainly tries to address these two limitations, and even though like you'll be seeing at the end of the talk, like we are not in a position to address this because like the situations were pretty different than when we thought about in the beginning. So to address these two limitations, so we did experiments over a simple preliminary investigations over a design Mach number of 2. So the nozzle was designed for Mach number 2. And the jet was expanded at different nozzle operating conditions, ranging from 3 to 8, which corresponds mostly to the overexpanded conditions. So, and in the starting phase of the work, so we started with the injectors. So the number of injectors, I'll just quickly go to the nomenclature in case like which might be of help for us in the forthcoming slides. So this is the injectors, and we call this is the nozzle pressure ratio which comes from the engine, and this injection pressure ratio is given by this IPR. Okay, and these are the number of injectors. So you can see like there are multiple looking at it. There are other parameters as the inclination of this particular injectors, the location, and a lot more parameters to handle it. So for the simplest case, what we took was like we took the 2 injector case. So we had 2 injectors. What you can see over here. This is what we call the number of injectors is 2. And the diameter ratio of the injectors was kept about like 0.08, which was pretty well with the literature, the data. So which was about like around this particular magnitude of. So D is the diameter of the injector, small d, and capital D the nozzle diameter. And then based on this injection pressure, so we varied it from 2 to 8. You can see like we wanted to constrain ourselves to the injection pressures of pretty less than the nozzle pressure ratio. So in a laboratory, we can also always exceed this. I can go to 10, 15, but as I said in the beginning of the slides, in practical situation, that's not always a viable solution. So we varied the injector pressure ratio from 2 to 8. So and the corresponding mass flow rates were about like 0 to 5%. Okay. And then the corresponding velocity ratio was somewhere about like 0.5 to 1.5. So in terms of the injection ratios. So this problem was slightly more parametric involved. So we started to look into a simpler problem. So we went with the single output system. In control theory, we call it as multiple input, single output system. So I can always look at the multiple output parameters since like it was the beginning stage of the work. So we started looking at the single output. So the output, what we were looking at is in terms of the supersonic core length, okay, which is well correlated to the jet mixing of the so the parameters which essentially plays for the supersonic jet, like we have taken the expansion ratio, the ideally expanded jet Mach number, and the species, that is the specific heat ratio, and then the parameter of influence from the flow control, that is the number of injectors, D by D is that's the injection diameter ratio, even though like which we didn't vary it, but we did vary for certain few cases for the validation of these scaling laws, which we'll be discussing in a few minutes. And then like these are the two parameters which essentially plays a role, that is the mass and the velocity ratio of the injections. Okay. So this is how a typical manipulation would look like, or a typical natural jet, like when this has been, like exposed to certain fluid conditions, like the shock structures are going to be manipulated. So we did certain images to understand, what actually goes on into the shock structure. So this is typically the control. Okay, this is for two different representation of the images for the overexpanded cases. And these are the cases where like we can see the fluid is being injected on both the sides. It's a symmetric injection. So when the mass flow rate was pretty much the same for different cases, like we say like there is a gross distortion in the shock structures, even though like this particular work was not interested to see what is actually going into the shock structure, but we see that, okay, there's going to be a strong changes in the shock structure. So this is essentially going to alter the parameter which we have discussed over here. That is the supersonic core length. So that is actually a measure of these particular distortions, even though like we haven't looked into. Yeah. So this injection, we just shifted it slightly because like if you see the first one, like because if we inject it somewhere over here, like we actually will include the thrust loss. There's going to be some percentage of the thrust loss. So we doesn't want to do that. So we thought like we'll just slightly shift it and try to see like without the thrust loss part. So the moment I try to inject any fluid over here, there's going to be a percentage of the thrust loss that one needs to account for. So in order to avoid those things, so we thought like we'll inject in downstream and the later cases proceed. So we'll look into the other cases as well. So to understand this particular scenario, so we thought of looking into the laws which govern such manipulation. So in order to address this injection pressure, which is less than nozzle pressure, so we developed a scaling law. So based on analysis, so we varied all those parameters, and then this particular function we actually proposed it to the analysis, and which is this MR is the momentum ratio, and you can see this suffix n corresponds to the momentum ratio of each injector. So here it's about 2 injectors. So in fact, like we have results with the other number of injectors, and probably that is why like even though like people would be surprised because this is for 2 injector case, and why should this n come in? So since this particular scaling law was developed for multiple number of injections, so this particular n takes care of the momentum ratio of each injector. And the momentum ratio is actually given by the expression of the mass times the velocity ratio, and this is essentially the pressure ratio that one would get in terms of the compressible phase. So this is what we plotted it. So we plotted the core length which we estimated it, and then like with comparison to this particular law which we developed. So all the data for the experiment running from NPR 3 to 8, like we have put out in this particular correlations, okay, and which was like deviating pretty much within this plus or minus 5% of the deviation. So then once we proposed this scaling law, so we wanted to look into, in a generic case, like we took the elliptic jet to be a well comparison, and because like typically elliptic jet is taken as the rough measures of better mixing. So using these laws which we developed it, so we try to predict what is this mass required to sort of match with the LC of the elliptic jet. So the LC of the elliptic jet was taken out from one of our previous work, which was a semi-empirical relation. So there was an expression which relates the LC to the elliptic jet aspect ratios and different Mach numbers and expansion ratios. So using those equations, like we were able to see what is the LC, and using the previous expressions, like we were able to predict like what is the mass that is really required to sort of mimic the elliptic jet. Even though this mimicking is only pertaining to the core length and not the global feature of the elliptic jet, because like a simple manipulation of a fluidic jet cannot actually replace an elliptic jet. So this was primarily only on looking into the supersonic core length part. So this was for one particular configuration. This is for the NPR of 4. So when we looked into the mass flow rate magnitudes with the aspect ratio of the elliptic jet, like running from one is the circle, and as it moves to the higher magnitude, it goes to the elliptic jet. And so if you see like the condition which we impose, like the IPR has to be very less than the NPR, because the NPR was 4 for this % data. So if you see on the right hand side, for each of the every magnitudes of CM. This is the corresponding IPR, which you can see over here. So this green shaded corresponds to the cap of 4, because like where it exactly matches with the IPR. So all the data over here, like corresponding to all these conditions corresponds to the IPR is pretty large. So as I said in the beginning of the slide, so the IPR has to be sufficiently lower in case if you want to put in for practical application. So what actually happens is like the moment I try to mimic an elliptic jet using this particular scaling law, it says that, I cannot go to an aspect ratio of 3 primarily because the injection pressure is going to exceed the nozzle pressure ratio. So this actually poses a serious problem for us. So we thought of like to handle it. So the bridge which came to help us was the scaling law, which we proposed in our previous slide. So using the scaling law, which essentially conveys that like what I need is the momentum ratio. It's not the mass or it's not the velocity ratio. I need the momentum ratio. So if I want to match the momentum ratio, I can always play with this particular mass. So if I can sort of vary the injection diameter, probably I can lower down this IPR. So if I want to bring down this magnitude, let's say from 4.9 to 3.9, only thing is that I need to switch over to a different diameter. Okay, but what is the different diameter is a question, so that can be predicted from this scaling. And in fact, like this was only for one particular configuration of NPR. So, but one of the interesting thing what we can actually see from here is like fluidic injections can actually replace the conventional elliptic jet in case like if I want to mimic different aspect ratios. So just by like changing the mass flow rate of the injectors, I can actually sort of mimic different elliptic jets by simple means. Okay, and if I don't want it, I can switch off the injectors and it will go back to the original shape of the circular jet. So that was one advantage of fluidic injection. So in order to predict like what is the best diameter, like let's say like for fluidic injections, keeping on the constraints that we have discussed in the first slide. So to predict optimal diameter, again, like we chose the maximum mixing. So we took the maximum conditions of the aspect ratio of the 4 elliptic jet. And this is the nozzle operating conditions, like, like if at all, like if you want to vary the operating conditions, so let's say from 2.5 to 7. And this is the diameter ratio, which is predicted from the scaling equation, which is given in the previous slide. And these contours are corresponding to the IPR magnitudes, that is the injection pressure ratio. So if you see like these symbols, the square symbols correspond to the condition where like the IPR and the NPR are the same. So if you see like below this curve, like the IPR magnitudes are pretty large. Let's say like if I want to operate an engine at NPR of 4, what I need an if I choose a diameter of let's say 0.1, like I might need an IPR of close to about 7. So the IPR is significantly larger. So the data below this curve corresponds to the IPR greater than NPR, and the top of it is the other way around, which is the IPR is less than the nozzle pressure. So on a global sense, what I see is like if I choose a diameter over this particular curve, okay, that is going to be the optimal diameter. But the catch over here is like, let's say in a fluidic injection, I cannot vary the injection diameter similar to an elliptic jet. As similar to I cannot vary the elliptic jet configurations, I cannot vary the injection diameter. So nobody is going to buy that. So I need to choose some optimal conditions which would actually perform for the entire range of operating conditions. So if I do that, the best diameter, what I need to choose is based on purely on the maximum limiting conditions. Let's say like I fix my engine that should operate for the maximum NPR of 8, and that is where the optimal diameter has to be freeze and not the minimum condition. And if I take about the minimum conditions, let's say like 0.12, if you see over here, if I chop it at this particular point, and for certain cases, you will see like you'll have an injection pressure less than the nozzle pressure, but for rest of the scenario over here is like the best diameter or the optimal diameter can be predicted, but that primarily depends upon the maximum nozzle operating conditions. But if I increase the diameter, let's say from 0.12 to 0.22, the penalty which I'm going to pay is the mass. So since in the beginning of the slide, it's like 5% of the mass. Since by increasing the diameter, what the penalty I'm going to face is I'm increasing the mass. But the advantage is like IPR can be always be kept less than 1. Okay, that is one advantage of it. So the next thing what we looked at was like, what happens if I say like, no, I don't want to mimic an aspect ratio of 4. Let's say I want to increase it to 5. If I do that, like let's say like the mixing or the benefits, if I want to slightly push it to the extreme, what actually happens is like the injection diameter is again going to be increased. So if I want to design any fluidic injection for some application, so what I need to look at is like, what is the maximum operating conditions and what is the maximum benefits I wanted. So if these things can be put into if this thing can be decided, then one can predict the optimal conditions. But the catch over here is like 0.26. Injection diameter of 0.26 is like, it's pretty a large number. So these are the preliminary investigations that we have carried out. And coming to the conclusions, as I said, like this, even though the injection diameter is 0.26 or 0.25, that has to be reduced down to 0.1 or 0.2 if I want to really put into use. That is what like we are planning in the future. So we are actually working on those things. But few takeaway from this particular talk is like fluidic injections can actually replace the conventional passive techniques because of like I can always switch on and off it like only if it is really required. If I don't want it, let's say during cruise, if I want to start, if I don't want a technique like similar like what we see in the commercial chevrons, if I don't want the chevron, like you cannot throw it during mid-air. But I can always switch off the fluidic injections. I can fly safe. Okay. So that is one advantage of fluidic injections. Okay. So to address this particular limitations, what we saw, so we actually proposed a scaling law. And this scaling law actually conveys that, like, like what are the conditions that has to be taken care, like when designing and injectors for application, full scale application. But as I said, like in the beginning of the slide, so we are not able to meet this particular conditions, even though like we are able to satisfy the injection pressures based on the scaling law. But we are not able to meet this particular conditions. Like if you can actually quickly see over here, the CM when based on the optimal condition of 0.22, let's say the diameter, the CM is going to be like close to 5%. And if I increase it, the mixing to be larger, then the CM is going to be increased further. So one of the key challenge for us in the future work is like, even though like we're able to satisfy the limitation number 1, but the limitation number 2 is still in hold for us. So we haven't actually tackled it. So even though like this can be met, the only thing is that CM might shoot up to 10% depending upon the scenarios. But ultimately, if I can make a compromise on it, let's say like, okay, I'm happy with this particular limitations. Okay, fine, limitation 2 doesn't matter, then probably like the injection diameter of 0.22 is a good take. But if at all, like if I say no, like CM has to be dropped down to some magnitude, then we have to look into different problems. We are actually working on those problems now. So that is where like we might lead to us in future. So thanks for listening. So any queries? So I'm good to take.
So that's a very interesting work. Can you go to the slide where you show the Schlerin image?
This?
The next one. So here I didn't understand what exactly you're comparing here with.
Okay, so this is where like we haven't done anything. This is a simple jet. Okay, so that's without manipulation. And the moment we try to inject fluid, okay, this is primarily at the exit of the nozzle. So the moment you try to do it, like there's going to be a change in the shock structure. So if you see like it was a sort of a regular reflection and you're converting it into a sort of a matrix. So all those things actually happen because as I said, like we haven't looked into it because the primary idea of this was to see like if we can propose some scaling laws and predict the diameters. Because as I said, like in the first slide, if you see like most of the works like which was mostly focused on this IPR, which was pretty much greater than the nozzle pressure, and the diameter was like 0.08 or something. But they haven't looked into the reason like why they kept diameter of 0.08 and why didn't they vary the diameters, and like haven't looked into the constraints of these two things. So this work actually focused on those limitations. But this images like we haven't, what we observed was like this injection is going to sort of like change the shock structure. As I said in the limitations, like if you want to put it here, the CM of 10% or something. If I want to reduce it to 5%, the only way which, but the penalty is the first I have to optimize it.
Okay, so what you have to the left is a numerical Schlerin, is it?
Yeah, this is without the injections.
And is it numerical Schlerin?
No, this is the experimental. The entire data is from the experimental.
Okay, because the contrast was slightly different.
Yeah,
so I thought.
because these were taken at different times and like we were not able to get it at same contrast.
Okay, but you said you mentioned that it weakens the strength.
Yeah.
But a regular reflection is
no, only here.
becoming
Like
max
if you see, like
reflection.
after the first auction, okay, so when we took the pressure data to it, and we said like the pressure magnitude was pretty low. So what I mean is like this particular change is somewhat significant over here. But when I move down the first rock cells, like it's completely weakened.
Oh, okay.
Hi. First simple question. That is like when you are trying to do this, you have introduced a new device
Yeah.
in there, right? Some protrusion,
solid protrusion
in some sense, right? That's just outside the shear layer,
Yeah.
right? So it is also going to affect your flow, right?
Yeah, but we have looked into it, like we did some measurements. Okay. So one is like without injections. Okay. Without injections means there was no flow, but the injectors were there. So the
Yeah, but
solid
that's
object
what
was
you
there.
should compare here, right?
Yeah, we compared it, but this is with the flow. But what experiments we did was like there was no flow, but the solid protrusions were there. So just to see whether the solid protrusion is going to interfere with the shear layer and it's going to make any changes. So we did those measurements. Okay. The location where we placed, we made sure that like that is not actually interfering with the shear layer. So
Okay.
we took the pressure data and we actually cross-checked those things.
Yeah, but if you have to compare, that's what I would expect to compare across.
No, this
But
was primarily
anyways,
because of the injections I want to show. So the only thing is that, like, let's say if you put an injector, the shock structure is not going to change. We have seen that.
okay. Next thing, I'm thinking much beyond this. Like, if you want to control a supersonic flow, typically you can control it with pressure or with velocity conditions. Okay. This looks like a pressure based,
Yeah.
you're forcing a pressure at the end of the jet, right? So can't you try something else? Just send a jet along the flow and then get a shear layer getting affected. And because of that, you can get some change.
Yeah, actually we are moving in that direction because there's limitations of CM. So because like CM is quite large because of this injection configuration.
No, only when you need pressure, you will need high pressures to come in, right? If you do the other one, you may not require so much.
Yeah, so that can be also be explored. Okay. But we haven't thought about it. But look.
That will make it easier. Or maybe you can put some small surface that's like tangential to the shear. Just bring it in slowly. And that may also change things faster. Yeah, that's like some kind of Coanda effect kind of stuff.
Yeah,
may come in
exactly.
there.
But they're using for the vectoring part. So
Yeah. But isn't vectoring your main target?
no, not here. So
What are you trying to achieve here?
so here, like we are trying to mimic the elliptic jet in terms of the mixing. So this primary investigation was for the acoustics. So we are actually performing the acoustics part of it.
It's only acoustics.
This is actually we are moving towards the acoustic part.
Okay, thank you.
A few questions and a comment. So in this picture, how would you define your LC star?
So like, okay, not from the, we have taken the LC star, not from the images. So we have taken the pressure data. So, and we have located like where the sonic conditions actually, forms. So once I have the data along the center line, so we look into the data where the supersonic flow translates to subsonic and we take that locations.
Okay.
So that is on the pressure data.
Okay. Okay. So that's one. So you are essentially predicating everything based off of what is happening at the center line.
Yeah.
Right. Okay, good. The second question I had was on your scaling, that you had your CM times velocity magnitude. And your point was that if you want to create a greater effect, you just shrink the diameter.
Yeah.
The issue with doing that is you're essentially creating perturbations at smaller and smaller circumferential area. And at the limit of 0, you're just essentially not creating anything. So effectively, you might argue that you can change the velocity by you are reducing the scale over which the perturbations happen.
Yeah.
So I question how much that effect is going to be. That's
Okay.
something I
So-
wonder about.
So that is like, for example, like I'll put it in a different sense. Like this, we varied the number of injectors. Okay, so let's see like like what is the interference of this number of injectors. So the moment we try to vary the number of injectors, like this equation was pretty much the same. There was no other factor apart from this momentum ratio. But if you look at the subsonic case, like we do have an effect of those things. So similarly, as I said, like if you want to decrease it, that's not going to influence this particular equation. There's no going to be effect of those particular interference.
So I'm not talking about increasing the number of.
No, like in the sense, like if I
injectors.
decrease or increase it, what at the end of the day is going to play is only this particular momentum ratio. So those so-called like going down to 0 magnitude is not going to change the functions.
Okay. Okay. The so that was number 2. And can you flip over a couple of more slides?
Yeah.
Yeah, I didn't quite understand what you are actually trying to do with this elliptical jet
Okay,
thing.
so elliptical jet is believed to be like, you can get the maximum mixing when compared to this circular jet. So we need something to sort of, like predict it. We need some benchmark. So the benchmark we took as the elliptic jet. Like, let's say like if I work on acoustics, I can say like, I need reduction in 10 decibels or 5 decibels. I can keep some magnitudes. So here, like, rather than keeping, okay, I want a jet mixing of some fraction. So we kept that limiting as the elliptic jet. So elliptic jet was taken for a reference.
Okay, and my last thing was more of a comment. May take it or leave it. So you made a comment that this one you can turn on and off the jet, unlike a chevron, which is a passive and
Yeah, but still there are variable chevrons also.
it creates a parasitic drag. But what I would also argue is when you have this, you are carrying all the infrastructure with you.
Exactly.
So you are still creating a parasitic drag, even though you turn on and off the jet, but you are still not away from out of the woods on that.
So
jet.
this is one of the
Just a
key,
comment.
this is one of the key challenges in fluidic injection, like system implementation. So that is, we haven't worked on it, but people are working on system implementation. The problem is like all those things. But what I can argue over here is like fluidic injections, like the parameter what we have used is primarily on the metrics of mixing. But we haven't taken into account of what is the energy supplied to it, because you need an energy to it. So that we have actually worked on it and we have actually submitted it. So rather than quantifying based on the core length, we have proposed expressions to weigh the benefits of the energy. Let's say like I pump 5% of the energy and get some mixing. So should I pump 5% or 1%? So on the similar lines, we have worked on it. So, but we haven't moved into those issues, like as you said, the parasitic drag and the system implementation limits. But we are slowly moving forward. So that's what I can comment on.
Good. Any more question? Yes, one clarification. Since everything you're done on the free jet, no, this correlation, does it valid if you do the injection inside the nozzle where the boundary conditions are different?
The equations are going to be different. Means like the same, the loss can be the same. I mean, the scaling loss can still remain the same with some minor modifications, but the equations are going to be entirely different. That is what will define this particular conditions of this diameter. So that those equations will define the magnitude of the diameter.
Thank you.
Yeah. Thanks.
Next speaker, Pradeep Gupta. It is study on unsteady shock. Study on unsteady shock motion in the diffuser section of a supersonic ejector. Online. I think he is joining online. Please carry on.
Hello, good morning to everybody. I'm Pradeep Gupta, postdoctoral researcher at Indian Institute of Science, Bangalore. In this symposium, I'm going to speak about unsteady shock motion in the diffuser of a supersonic ejector. So this is the content. I'll start with the introduction of a supersonic ejector, the different application and flow regions of an ejector, followed by the motivation and objective. Then I'll speak about the experimental setup at Laboratory for Hypersonic and Short Wave Research, ISC Bangalore. Then how we have obtained the short leading edge location of the short structures and associated dominant frequencies and amplitude of those with short structures. And this talk will be concluded by summary and references. So this is the schematic of an supersonic ejector where we have two different fluid at different pressures. So the red one is the high pressure fluid, and we termed as a primary fluid, while the blue color is the low pressure fluid, and we termed them as a secondary fluid. The primary fluid enters in the ejector through one CD nozzle, where it shows that the nozzle throat and expands as a supersonic velocity at, in the diverging section of the nozzle. The high velocity of the primary flow creates a low pressure region that allows secondary flow to come in the ejector from the ambient. The primary, in this case, the primary nozzle operates in the under-expanded mode, and that's why the primary flow further expand in the mid-syn duct of the ejector. The expansion of the primary flow creates the constrained path for the secondary flow, where it accelerates the secondary flow to sonic velocities. Then primary and secondary flow meets in the mid-syn duct by means of the shear layer, expansion and short wave in the mid-syn duct. Mid-syn of the supersonic primary flow and the sonic secondary flow results in the supersonic mid flow towards the end of the mid-syn duct. And we know that if the supersonic flow encounters a diverging section, it forms the shot, and the shot interacts with the boundary layer, and we have the set of shot we term as a shot train. Here, these shot trains mainly form because of the high back pressure at the end of the ejector, so we term them as a recompression shot structure. So shot structure here result in the pressure rise and turns the supersonic flow into subsonic, and subsonic flow further expand in the diffuser section to pressurize or the pressure recovery. So this ejector works on the principle of thermal compression, means it does not require any mechanical power to produce the compression effect. It does not consist of any moving part, and hence requires less maintenance. And also we have the very simple geometry like this varying area duct. Owing to these advantages, ejector has been utilized in various aerospace application and energy application. In aerospace application, it has been used in pulse detonation engine, ramjet, scramjet, high altitude test facility for producing this low or vacuum, and we can test. Ejectors are used to for vacuum generation, and that can be used for high altitude test facility. Wind tunnel testing we are using. Thrust dimension we can use as ejector to increase the thrust for the eject engines. And in the energy one, we are using the vapor ejector refrigeration system, transcritical CO2 refrigeration system, supercritical power systems, fuel cell, anodic recirculation, and power plants. So this is the working principle where the primary flow at high pressure enters in the ejector at the nozzle throat, then accelerate to the supersonic velocity in the diverging section, and the primary flow expand and accelerate to the secondary flow to sonic condition at virtual throat. Then primary and secondary flow mixes in the mid-syn duct. The supersonic velocity, supersonic mix flow expand in the diffuser and velocity increases, and then we have the normal shot which decelerate the flow to the subsonic, and the gradual pressure rise or pressure recovery takes place in the diffuser. As I mentioned, the expansion of the primary flow accelerate the secondary flow to the sonic condition at the virtual throat. So in few cases, when the expansion of the primary flow is not sufficient, so secondary flow remain unchoked in the mid-syn duct. So based on the secondary flow choking, ejector operation has been divided into regions called the critical flow region and the mid-flow region. In the critical flow region, since both the flows are choked, they carry their maximum mass flow rate, and increment ratio, which is defined as the secondary mass flow rate to the primary mass flow rate, remain constant, as though both mass flow rates are constant for the critical mode operation. On the other hand, for the mixed flow mode operation, primary flow only choked at the nozzle throat, while secondary flow remain unchoked. So increasing the back pressure or compression ratio result in the detriment in the secondary mass flow rate, or in turns increment ratio as shown here in this plot. Reverse flow, when primary flow itself does not choke and primary flow enters in the ejector and may come out from the secondary inlet. The critical back pressure is defined as the maximum pressure till when the ejector operates in the critical mode operation. So this is the flow structure for the critical mode operation and the mixed mode operation, where we can see the recompression shot in the diffuser. That indicates the flow is supersonic in the mid-syn duct, and that in turn indicates the secondary flow will choke somewhere in the mid-syn duct. The location of mid-syn duct still is open problem, and here we cannot identify where the secondary flow chokes. On the other case, in mid flow region, there was no shot structure in the diffuser, and flow remains subsonic after mid-syn. These are the characteristics of the flow region based on the pressure, mass flow rate and the pressure measurement. So if you consider this SPR, which is the stagnation pressure ratio, defined as the primary stagnation pressure to the secondary stagnation pressure, we can see around 1.45, the increment ratio remains constant and then it decreases. So this is the characteristics of the critical flow region, and this decrease in increment ratio is characteristics of the mixed mode operation. So due to the consistent performance in the critical mode, we had focused this study on the critical mode operation, and we looked on the SAT structure present in the diffuser section. And this is that pressure measurement. So as I mentioned that in the critical mode operation, primary flow expansion is severe, and we can see the primary flow expand till around 60 APA. And further increase in this pressure the response to the mixing of the primary and secondary flow, and flow becomes supersonic at the diffuser inlet, and this decrement in the pressure the response to the expansion of the supersonic mixed flow in the diffuser, and rise in pressure is due to the recompression SAT structure, and this gradual pressure rise due to the subsonic flow expansion in the diffuser. Here we did not see any significant drop in the primary flow, while this increase in the pressure corresponds to the mixing of the primary and secondary flow, and this gradual rise in pressure corresponds to the expansion of the subsonic mixed flow in the diffuser. Literature review. So Devrot and Safarit has studied the transonic instability in the supersonic ejector in the mixing bed. So supersonic ejector means here that primary as well as secondary flow both are supersonic at the nozzle edge, while in the ejector the secondary flow is subsonic and the primary flow is supersonic at the nozzle edge. So these are the basic SAT interaction, and they found they have done FFT over this Celerian images and found this the dominant frequencies were 63 hertz. As per the ejector concern, this Rao and Jagdish has performed unsteady oscillation for the ejector in the mixing that, not in the diffuser, since there were no SAT structure in the diffuser because ejector operates in the mixed mode operation. So in the studying the SAT oscillation in the mixing that, they found the frequency were less than 100 hertz, and the amplitude of the frequency were height of the nozzle eject. Now, based on this one, we just frame out our motivation and objective of the current work. So as I explained, the critical mode operation offers the consistent performance and thereby have been implemented in various energy and aerospace applications. But no study were performed for the dynamic SAT structure in the diffuser for critical mode operation. And due to the SAT oscillation, the fatal load in others, and that may lead to the structural failure of ejector. So it is essential to study the dynamic behavior of the SAT structure. Objective of this work is that will estimate the leading SAT location from the captured Celerian images, and will characterize the dominant frequency and associated amplitude of these SAT structures. So this is the schematic of supersonic jet facility at Laboratory for Hypersonic and SAT wave research. So we have a compressor, screw compressor, air dryer for producing dry air. Screw compressor can produce air up to 12 bar, which we can store in the air receivers. The primary flow enters through primary nozzle via pressure regulator, where we can control the primary flow pressure. And for this study, we had changed primary flow pressure from 489 to 989 kPa. We had used 3 different primary nozzle as well, having the Mach number of 1.5, 2, and 2.5. This is the Celerian setup where we had used this SILEX 640 light source, which is the nano pulse with the pulse width of 10 micron. Tantheometers has a focal length of 3 meter. We had used phantom mirror camera, which captured the Celerian images with 10,000 hertz. Along with the this Schlieren arrangement, we had done the pressure measurement along this ejector, and we had 19 different pressure sports along this ejector from the nozzle edge in the diffuser. And we had used piezoresistive MPH 4250 pressure sensors and piezoisotope as the data acquisition system. The sampling rate for the pressure measurement are then 10,000 hertz, and test time is about 3 seconds. So this is that the experimental component at LHSR. So we have compressor, receivers. This is test section. This is the pressure sensor, DRAT, mirror camera, and this stylet slide source. So this is the pressure signals for the few sensors. So one sensor is located in the mixing duct, another 3 are in the diffuser section. So the pressure fluctuation on the in the pressure signal of pressure which is located in the mixing duct is comparatively low. These fluctuations correspond to the turbulence mixing of the primary and secondary flow in the mixing duct. While in the case of pressure signals in the diffuser section 180, 210, and 240, the pressure fluctuation is order of around 25% of the mean pressure itself. That suggests that indicates that SAT is moving in the diffuser section. So here we can clearly see we had focused our viewing area in the diffuser section from 180 to 250 from the nozzle edge. So this is the primary SAT, and we have expansion wave and the secondary SAT clearly seen. And here we had marked the primary SAT, this is SAT structure, and these are the expansion wave, and this is the secondary SAT. These 3 images corresponds to the nozzle 1, 2, and 3, 1.5, 2, and 2.5. In the and this is with the vertical knife edge orientation, where we the boundary layer and the suppression bubble was not very clearly visible. So we changed the knife edge orientation to horizontal. And in these images, we could see the boundary layer and the suppression bubble when the boundary layer interact with the this SAT structure, this suppression bubble. And we try to locate the SAT, the leading SAT edge rotation. So we write a code on MATLAB platform based on the tiny edge detection technique, and we had marked this leading SAT leading edge at different time instants. So here we had plotted the distance of the leading SAT location for 2,500 images. And here we can see the SAT motion started from something around 185 to around 225. So the amplitude of SAT is around 40 mm, which is almost 3 times of the mixing duct height in this case. So we performed for this is that FFT of the trace SAT location from the Schlieren images. Here we can see this the frequency associated with the SAT waves are multimodal with frequency ranges from 83 to 175 mm. So and also we had done the dynamic pressure measurement. We had performed this FFT on the dynamic pressure measurement for the 4 different sensors in the diffuser 160, 180, 210, and 240 mm. With these images also, we see this frequencies, our dominant frequencies lie between 90 to 194. The frequency range from this Schlieren method and pressure measurement are almost similar. So this comes to the summary of this presentation. So we have seen these ejectors are a passive device that compresses low pressure fluid by utilizing the pressure energy of tow flow in high pressure fluid. Decompression SAT structures are observed for the critical mode operation, indicating mixed flow is supersonic at entry of diffuser. Decompression SAT structures are oscillating with an amplitude approximately 3 times of the mixing duct height. Dominant frequency estimated from pressure and Schlieren images are multimodal with frequencies ranging between 80 to 200 Hertz. The similar frequency ranges from the pressure measurement and Schlieren images indicates that dominant frequency of SAT structure can be well estimated from the pressure measurement in cases where Slurry images are not, or slurry images is difficult, like the circular geometry or so. So I would like to acknowledge my PhD advisor, Dr. Srisaram and Professor Pramod Kumar, Professor Jagdish Dopalan, the in charge of LHSR lab, and this lab mates Sanjay, Bala, and Ramji, who helped me during the experiment, and other students and staff of the LHSR. So these are the references. Thank you.
Okay. Any clarification?
Hi, Pradeep.
Hi.
I have a few questions regarding the applications aspect that you mentioned. So
Okay.
you said that this ejector design can be incorporated into ramjet or a scramjet design, right?
Yes.
In the initial slides. So I'm curious, what is it that the introduction of the second flow, what advantage is it bringing to the table? Is it in terms of better thrust or compression, pressure ratio? Or what is it?
Basically, I think it increases the thrust slightly. So I didn't do more detail on this application, but as I know, this increases the thrust of the engine. I'll refer the paper where I have taken from, so I think you can just have a look on that.
Okay. My second question is, so I'm not very familiar with the literature associated with these ejector studies. So you mentioned that there are a few dominant frequencies and shock oscillations that show up because of the introduction of this secondary flow. And so if you were to incorporate this into a scramjet or a ramjet engine, so if the secondary flow was absent, there won't be any oscillations, right? Is it triggered by the introduction of the secondary flow?
I think even this if there is no secondary flow, there should be oscillation. I think that work by this Arun sir and Rajesh sir is they have moved completely the secondary this thing, but still I think the SAT I think there is no SAT in the diffuser, but SAT would be present in the MITS in that, and that would be oscillating. I think there should not be any SAT in the diffuser section in the piece when we don't have any secondary flow.
Because if the oscillations are triggered by this, then it may not be of much help in a ramjet or a scramjet engine, because that might also, the shock oscillations might.
No, then it may tease that for this scramjet and ramjet, ejector might operate in the MITS mode operation. So in the MITS mode operation, there was no oscillation in the diffuser section. So for the critical mode operation, where I have focus, and that is more in the application in the energy sector, where we need a consistent performance. So in the scramjet perspective, ejector may operate in the MITS mode operation, and there is no SAT oscillation in the diffuser. So whatever this presentation deals with this critical mode only. So there are two modes. So other the ejector operate ejector application in the scramjet may be in the MITS mode operation.
Okay. Okay. Thank you.
Any more? I wanted to have one clarification. This fluctuating pressure amplitude, no, in the mixing duct, it is lower than the incoming thing. One would expect a little higher, the mixing duct where the shocks are there, interaction is there with the subsonic flow. Why it is lower compared to the incoming flow?
Can you repeat once again, sir? I could not get
Pressure
the
fluctuation amplitude you have plotted now with respect to different.
Yes.
Where you are shown, this one.
Yes.
Next one, not this. One more.
This is the-
They're up. Not this. No. Please go up.
Here?
Further. Yeah. This
Yes.
one, yeah. That is with respect to time, is it?
Yes, sir.
Okay, fine. If no more question, I think we can thank him.
Thank you, sir.
We have come to end of the sessions. I think we had 3 papers. All the 3 papers describing 3 different problems of different type of shock interaction. One is external, other one is diffuser, other one is the mixing of the primary with the secondary jets. All of them are interesting. We reasonably thank the organizers for completing it exactly at 12 o'clock. Thank you.
I would like to invite Professor Nagamudra, sir, Department of Aerospace Engineering, IIT Madras, to present a memento to the session chair, Pandian, sir. We have successfully reached the end of all the technical sessions of the 24th International Shock Interaction Symposium, SIS-2022. We thank all the professors, delegates, research scholars, and students who have graced the event with their presence at IIT Madras. Now I invite Professor G. Rajesh, Conference Chair, SIS-2022, to give an announcement about the next International Shock Interaction Symposium.
Thanks, Ramachandra. So can you just display it here? Zoom link. Yeah, it has been a custom in all the symposia that we will announce the next symposium. We will call the next symposium chair to the meeting to invite all the delegates attending the next symposium. I would like to invite Professor Schreiger from TU Delft, Netherlands. Yeah, good morning, Professor Schreiger. Yeah, you can make a small presentation on the next symposium to be held in Netherlands in 2024.
Okay, can you hear me?
Yes, we can hear you.
Perfect. Good morning, everyone, and or maybe good afternoon to you. Good morning to us here in the Netherlands. It's 8:30 here, so you're already way ahead of us. I've prepared a little presentation to welcome you to Delft. So let me share my screen. Here we go. Okay, so we're very happy that we can participate in the organization of the International Shock Interaction Symposium. And today I want to give you a flavor of what you can expect and where the symposium will be held. So I will be organizing the symposium together with my colleague Bas van Oudheusden, and later on also some other colleagues from our group. So we are very happy to be able to welcome you in 2 years at the Technical University of Delft. It's basically the biggest technical university of the Netherlands. So it comprises of 8 faculties, almost 6,000 staff members, almost shy of more than 25,000 students. And here on the right, let me enable my pointer. Here on the right, you see a picture of the campus. And more specifically, we will host you at our Faculty of Aerospace Engineering. It's basically it's the only Faculty of Aerospace Engineering in the Netherlands. and we basically cover almost all engineering disciplines that are involved in aerospace engineering. We have approximately 200 staff, 300 PhDs, and just shy of 3,000 students. I think in Europe, we are one of the largest aerospace engineering faculties. The idea is to host the symposium inside the TU Delft Aerospace Engineering faculty building. It's a very inspiring, say, environment. As you see here on the top right, we have our entrance where we have all kinds of attributes related to aerospace, also to high-speed flight. In the bottom right corner, you see a Vulcan engine, say unused one, of course. Inside our faculty, we have ample room to host the lectures. Of course, in addition to, and I hope this will not be necessary because we much more like to have the interaction in person. But in addition to having on-site presentations, like also excellently was done in this conference, we will also host a hybrid option such that we can allow for a live stream. All our rooms are basically made, say, compatible with live streaming, also for lectures that we use nowadays. So our proposed date to hold the event would be in summer. I have understood that in Madras it can be quite hot during summer. Here it's not so hot. In fact, it's the most pleasurable time to be around. So we propose to have a provisional date somewhere in, say, beginning of July, when our exams have finished and all rooms are available. Have a very similar conference program of 4 days with 1 to 2 keynotes a day, a welcome cocktail, a conference dinner plus social event, and also some scientific lab visits. At the faculty, we have a number of experimental and facilities, wind tunnels, but also other facilities. And there is also the opportunity to go to our National Aerospace Research Institute and also to a German-Dutch wind tunnel company that has one of the largest wind tunnels in Northern Europe, not very far away from us. So Delft, you can see here a picture of the Netherlands. It's a very, very small country. And we are located close by in a region which is called the Randstad, which is basically where all the large cities of the Netherlands are. We're basically just adjacent to Rotterdam, Den Haag. That's where our parliament is present, and Amsterdam is only 50 kilometers away. The easiest way to reach Delft is from international is of course through Schiphol, our main airport, and of course for people closer by, you can also come by train. There is an excellent train service, high-speed trains coming from Brussels, Paris, and London. So Delft, here you see some pictures of our small city. It's very characteristic of the Netherlands. It's from the 17th century. You see on the top left, you see our town hall, which was basically from that period, and also the main square. Delft is very well known for its pottery, where we basically copied the china that used to originate from China. And on the bottom, you see this is a typical picture of the rest of the city, where you see the canals and the abundance of bikes that you will find around. So this might be, for those of you visiting Delft for the first time, or the Netherlands for the first time, this is something to watch out for, because it's very easy to get hit by a bike in our small city. Delft is also known for its painters. There is Johannes Vermeer. He's very famous. Top right, you see a picture of him. In fact, this picture, you see a church on the top right there as well, which is basically the church at our main square. So this is a view from the harbor toward Delft. but also on we have the famous painting with the girl with the pearl earring. And in addition to that, one of the fathers of microbiology, Anthony van Leeuwenhoek, was also coming from Delft, where he was making his famous microscopes. Of course, next to Delft, as I already said, you have Rotterdam, which is quite a nice port. We will also see if we can maybe make an excursion to the port. There is, of course, Amsterdam with the abundance of musea, Van Gogh Museum, het Rijksmuseum. So there is a lot of stuff to see there. And of course, The Hague on the bottom left, we have the Dutch Parliament is housed there. And also there are a lot of, it's also an old city where there is a lot of stuff to see. And of course, I couldn't mention the Netherlands without mentioning the windmills. Also close by to Delft is the famous Kinderdijk, where there is a dike where there are numerous windmills that were used to basically get rid of all the water such that our feet would stay dry. So there is also, apart from the symposium, a lot of things. Concerning the committee for the symposium, it will consist of the following people. I will host it together with my colleague Bas van Oudhuisden, but there will also be two other colleagues from our group that will be co-hosting. That will be Professor Stefan Hickel. He's an expert in high fidelity simulations, together with Davide Modesti. And we will also have support from our secretary, Ms. Colette Russo. Finally, we'll also look for some sponsors. Of course, our typical sponsors are TU Delft and the Faculty of Aerospace Engineering, but we will also explore to get some contributions from ERCOFTAC and also from our local research school, the JMBC Burger Center. It's a research school for fluid mechanics. And we will also have a look whether we can attract some industry and also some exhibitors. So basically, this is my last slide to introduce you to Delft, to the TU Delft, to the city of Delft. And yeah, we hope that you are all interested in coming here and having, like in the present conference, a fruitful discussion on everything that involves shockwaves and high-speed flows.
Thank you, Professor Sridhar, for that wonderful presentation. So next, I would like to call Professor Shisha Rao to announce the NSSW 27th NSW to be held in PRL Ahmedabad. The symposium chair is Professor Balamurugan, but he's not here. So I'd like to call Dr. Shisha Rao for announcing that.
Good afternoon. So, yeah, I think we had a wonderful session over the shock interaction symposium, and a lot of interesting presentations. And sort of past 2 years, we have not been able to have interactions. As I think after the current break, we are having a lot of interactions. And so the coming year, as mentioned earlier on during the inauguration, 2023 will be quite busy for the high-speed community. We'll be having our national shockwave symposium, which is going to be organized by PRL in Ahmedabad, and I am announcing actually already the announcement is out for this symposium, and we are seeking abstracts. This is also co-hosted by the Society of for Shockwave Research India, and and so we will be looking at all the themes on shockwaves, high-speed flows, application of shockwaves, industrial applications, medical applications, and so on. The preceding National Shockwave Symposiums garnered more than 200 papers from all around India, and we expect similar response from our colleagues throughout the country. So welcome to the conference, and please contribute in large numbers. Thank you.
Thank you, Professor Shisha. So we'll be having the 34th International Symposium on Shockwaves next year in Korea. So Professor H.D. Kim is the chairman of that symposium. He is unable to join today. Instead of that, he has sent also sent a video to be playing for the symposium. Yeah. Please play that video.
Shockwave has been well known as a singular phenomenon typical in fluid engineering. Since its pioneering discovery by Ernst Mach in the late 1800s, the shockwave researches have been actively carried out, centered mainly on aerospace applications. The National Symposium on Shockwaves was first held in 1957 to promote the exchange of findings and academic information between researchers. After the inaugural symposium in the United States, 33 editions have been held successfully around the world. Shockwave phenomena is now being applied to a variety of engineering applications beyond aerospace that lead to new technologies and innovative devices. The ISSW has been integral to developing this research on shockwaves and associated technologies. And we are honored to carry on the tradition through the 34th ISSW to be held from July 16th to the 21st in 2023 at Daegu Exco, Korea. Exco is the optimal venue for a large-scale international event like ISSW. It comes equipped with world-class IT facilities, a variety of nearby amenities, accommodations, and dining options. Located just 20 minutes away from the airport and train station, convenient access for attendees is another advantage. The city of Daegu is Korea's center for education, culture, and industry. In the downtown area, attendees will find shopping centers and traditional markets, showcasing K-beauty and K-medicine, as well as restful public parks. UNESCO World Heritage Sites, so attendees can experience the best of Korea's traditional and modern culture. Furthermore, Daegu is home to global corporations like Samsung, LG, and Hyundai that can offer technical tours and insights into the latest industrial technologies during the symposium.
Good evening, good afternoon, and good morning, depending on where you are on. I'm Hee-dong Kim, the chairman of the 34th International Symposium on Shockwaves. On behalf of the local organizing committee, it is a great honor to welcome the 34th ISSW to Daegu, Korea. We are working hard with professional convention organizers to prepare a stimulating academic program and enjoyable cultural event for attendees. We hope that there will be no concern about COVID pandemic in 2023, but just in case, we will take all possible prevention measures and biomedical insurance for the participants. Also, we will be considering the hybrid format of the symposium. We are fully committed to making the symposium a grand success. I hope to see you in Daegu, Korea in 2023.
The 34th ISSW in Daegu promises to be a safe, secure, and memorable event for all attendees. We look forward to welcoming you in the summer of 2023.
So as I promised that the next year will be quite, so after ISSW, we also have, before ISSW, we have the AIAA Hypersonic Symposium, which is, a well reputed symposium regularly being held by the AIAA, American Institute for, American for Aeronautics and Astronautics. So we'll be hosting it in Bangalore, IISc Bangalore. The venue will be Hotel Grand Sheraton in Yeshwantpur, which is just outside Indian Institute of Science. So we welcome all members over here to that conference as well. It's going to be held between May 28th and June 1st of 2023. Welcome you all to the AIAA conference.
Now, I would like to invite Professor Jagdish Gopalan, the President of International Shockwave Institute and the Society for Shockwave Research, to share a few words about our SIS-2022 IIT Madras.
Thank you, Rajesh. Good afternoon to all of you. Am I audible?
Yes, sir, you are audible.
Okay. Thank you, Rajesh and Sriram and all the members of the organizing committee of Shock Interaction Symposium at IIT Chennai. Hearty congratulations on putting together a fantastic program. And everything went on like a clockwork, both the online presentations as well as the offline presentations, which I was fortunate to attend in the first 2 days. And this is very heartening to note that after the dull years that we had during the pandemic, we have put that behind, and the Indian shockwave community and the international shockwave community is again coming together to have these offline meetings. And I think it's going to be busy 2023 and 2024 for all of us. And I look forward to these interactions further. Thanks to Professor Srija for coming forward to host the next symposium. Welcome to the shockwave community. We are looking forward to visiting IU Delft. And I am also glad to acknowledge the presence of two of our stalwarts. So Berik Skews and Dr. Valenta, and even Dr. Marianne is also there on the online. And looking forward to seeing all of you again in, of course, there are 3 meetings that we are hosting next year, 2 in India and 1, of course, in the Shockwave Symposium that would be held in Daewoo. And let us all join together to make this community more vibrant. And I am sure that you would have many opportunity to interact together, living behind the tumultuous years of the pandemic. I thank all the volunteers, especially the student volunteers who are working in the laboratory of Professor Rajesh and Sriram. All of you did a fantastic job, and I think there is no substitute for offline meeting. You may have hours of interaction online, but I would rather love to have a few minutes of interaction in person. In that sense, I think this meeting has been a phenomenal success. I am sure that you will have more happening in the years to come. Thank you once again, Rajesh. Fantastic job done on behalf of the International Shockwave Institute and the international shockwave community. Please accept our heartiest thanks to all the student volunteers and the organizers of this wonderful symposium on shock interaction. So I would just like to applaud the wonderful role played by all of you. Thank you so much. Looking forward to seeing you in the future meetings in 2023 and beyond. Thank you.
Thank you, sir. About the conference. Online delegates also can share their experiences and feedback about the conference, if anyone is willing.
Yeah, we'll have the feedback getting collected during banquet also. Okay. So yeah, so now we are here at the end of the symposium technical sessions. We'll have only banquet left. Actually, it has been a great feeling for us to have all of you here. I've heard from you about the wonderful research that you are doing in shockwave research. We are very happy that the shockwave dynamic research takes new heights. Normally, the symposium is generally is for fundamental aspects of shock waves. All the years it has been like that. There used to be very rigorous interactions among faculty members. And I have seen that in this particular symposium, we have seen that the shock wave research has transformed into applied research. There were very wonderful papers on how shock waves and how shock waves can be used for many applications in high-speed flow area. And thank again all of you for being here, and I hope all of you have enjoyed the symposium both technically and personally. I also would like to thank the International Advisory Committee members of ISSW, especially Professor Beric Skews, who actually wanted to come over here, but due to the inability to travel, he was not able to join. But I saw him for the inaugural session, which was held on Monday at around 9 o'clock here. That means it is very early in South Africa, around 4:30. And he took all the pains to join from there at around 4:30 in the morning. So, and Professor Valanda has been there, and I see Professor Romang also there. So I would like to thank all my colleagues from the department and the institute for being here to support us, and also my friends. I also thank our director, head of the department, Professor Murthy, for being here on the inaugural day. And I thank special thanks to Mr. Kannan Krishnamurthy and his team for doing a wonderful job for the Zoom meeting and the live streaming. And I thank the ICSR facilities team for the excellent arrangement. Finally, I would like to tell you that all this would not have been possible with the wholehearted help from our team, myself and Sriram's students. Many times we were not here, we needed to be away from the institute, and they have planned each and everything, small thing meticulously, and made this symposium a great success. So those are the people who are the real heroes behind the scene. So I would like to thank all of them. And so they had a very great plan, be it the selection of the symposium tour venue or the buses to get transported there, and the pens, the bags, so everything in the kit. They only have decided that after long deliberations, actually. So I think it has been a really wonderful effort from all of them. And I would like to call all the coordinators to the stage to be with us, along with Professor Sriram. Please come to stage. I need not call by names. So we have Anbu, Shiva, Ramachandra, again another Shiva, Divya, Tara, Vinod, Srilal, Vishnu, Jabir. So Dr. Jabir, so join this. He is down with the very not here. So please give them a great applause. Kishore is also here. He is the man behind the camera. So can you just take a photograph? Sorry for keep you waiting for. Now I would like to, please be there, don't go. Please be there. Now I would like to invite all the delegates to the stage to have a photograph. Please come on to the stage or wherever we have a place. Sir. So with this, I announce the official closure of the symposium. Yeah. Now we will move for the banquet.
We please request everyone to stand up for the national anthem.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य चल यमुना गंगा उज्जल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
We kindly request the delegates who have registered for the banquet to stay back. Bus will be coming in a few minutes. We can all start together. Thank you. And we request everyone to have this card. So this QR will be used for the banquet. So kindly have this card. Thank you.